Quantum decoherence. So imagine you're holding a coin in your hand. You toss it into the air. In the real world, it lands as either heads or tails. But in the quantum world, something far stranger happens. The coin doesn't just choose one side while it's spinning in the air. In quantum mechanics, it actually lands on both sides at the same time. It enters what's called a superposition, and only when you look at it, when you observe it, it chooses heads or tails. That strange in-between state, that mystery, is where quantum decoherence lives. Let's slow it down a bit. Quantum decoherence is like the cosmic translator between two languages, the weird quantum world where particles exist in multiple states at once, and the world we live in, where a thing is just a thing. It's either this or that, not both. But how does that transition happen? Let's say we've got a particle. We'll call it Q. Now, Q isn't like a tennis ball or a marble. Q doesn't have a position in space the way normal objects do. Instead, it exists in a cloud of possibilities. It's here and there and somewhere in between all at once. It's only when you try to measure it, when you poke it, that Q suddenly snaps into a single definite state. That's weird, right? So where does decoherence come in? Decoherence is what happens when that tiny quantum system, like our particle Q, interacts with its surroundings. And surroundings could mean anything. A molecule of air, a stray photon, even your measuring device. The environment plays a role. The moment Q starts talking to the environment, something changes. That beautiful, delicate quantum superposition, poof, it unravels. But not because Q was forced to choose a state. No, decoherence isn't about collapsing anything. It's more like the system becomes entangled with the environment. The environment knows too much. It leaks information. And that destroys the interference, the thing that makes quantum systems act like they're in multiple states. You're left with something that looks classical, something boring, something that feels familiar. And here's the twist. Decoherence doesn't mean the quantum system chose a state. It just means we can't see the interference anymore. The quantum magic is still there, but it's become invisible to us. It's drowned in the noise of reality. Kind of spooky, huh? Here's an analogy. Think of a violin playing a pure note in a soundproof room. It rings out clear and vibrant. That's your quantum system in superposition. Now open the door and let in a crowd of people talking. The note gets buried. The melody is still playing, but you can't hear it anymore. The environment, the crowd, has caused the violin's music to decohere. Quantum systems are like that violin, and decoherence is the chatter of the universe. Now here's where it gets deep. Decoherence isn't just a curiosity. It's one of the big clues in understanding why our world seems classical, why we see apples fall and planets spin and people walk in straight lines, even though the universe underneath it all is built from quantum rules. Without decoherence, every particle could be in a superposition, every outcome coexisting. But thanks to the environment constantly interfering, we see just one version, one timeline, one reality. At least, that's what it looks like. Some interpretations, like the many worlds interpretation, say that decoherence doesn't eliminate the other possibilities. It just separates them. Each version of the outcome still exists in its own branch of the universe. So maybe, when you flipped that coin earlier, it landed heads here, but somewhere else, another you watched it land tails. Decoherence, in this view, doesn't delete the other outcomes. It just fences them off from each other. And because they can't interfere anymore, you never notice. Let's zoom out for a moment. Quantum decoherence helps physicists design better quantum computers. Why? Because these machines rely on quantum superpositions, but they're incredibly fragile. A single interaction with the environment, a vibration, a stray particle of heat, and boom, decoherence. The quantum information leaks. The magic disappears. That's why quantum systems need to be kept super cold, shielded, and isolated. Because decoherence is always lurking, waiting to turn your quantum miracle into a classical dud. So, what are we really saying? Decoherence doesn't destroy superposition. It doesn't force particles to choose. What it does is hide the quantum nature of things. It smears the interference. It makes the system look classical, not because it is, but because we've lost the ability to see the quantum pattern. It's like looking at stars through a fogged-up window. The light is still out there. You just can't focus on it anymore. And that's how the crisp logic of Newton's world emerges from the haze of quantum uncertainty. Some physicists say decoherence is the key to solving the measurement problem in quantum mechanics. Others think it's only part of the puzzle. But all agree it's one of the most important ideas bridging the two worlds, the quantum and the classical. So the next time you flip a coin, remember that, for a brief moment, it might have landed on every possible side at once. And the universe? It knew. The holographic principle. Okay, imagine this. You're holding a snow globe. You shake it. The glitter swirls around, catching the light, and inside that tiny glass world, a whole little scene plays out. Trees, a house, maybe even a tiny person. Now, imagine that entire 3D world inside the snow globe isn't really three-dimensional. What if everything inside it, space, time, gravity, even that little person, is just a projection from the surface? It sounds crazy, right? But that's exactly what the holographic principle suggests. It says that everything we experience in our 3D world might actually be encoded on a 2D surface at the edge of the universe. Yeah, like a cosmic hologram. It's not science fiction. This is a real idea in physics, a big one. And tonight, we're going to fall asleep thinking about it. Let's zoom in. A hologram in the everyday sense is something you've probably seen before, maybe on a credit card or a shiny sticker. It looks 3D, but if you touch it, it's totally flat. All that depth, all that detail, is just an illusion created by patterns of light. Now imagine that, but for the entire universe. Here's where things get mind-bending. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking were studying black holes, those mysterious objects in space where gravity is so strong, not even light can escape. They realized something odd. The amount of information or entropy that can be contained in a black hole isn't related to its volume. It's related to the area of its event horizon, the surface that surrounds it. Wait, what? That's like saying you can fit more data into a balloon based on its skin, not how much space is inside. Strange. But it made sense in the math, and it got people thinking, if black holes work that way, maybe the entire universe does too. Enter the holographic principle. In the 1990s, physicist Gerard T. Hooft and later Leonard Susskind proposed a radical idea. Maybe all the information in our 3D universe is actually stored on a distant 2D boundary, like the surface of a sphere surrounding us. Everything we see, everything we touch, all the galaxies and atoms and stars, just projections from that surface. In other words, the true reality might be written on the edge of the cosmos, and what we call reality is just the 3D shadow of that deeper information. Still with me? Good. Let's take it deeper. This principle got a big boost from string theory, one of the leading candidates for unifying gravity with quantum mechanics. In 1997, physicist Juan Maldacena proposed something called the AD-CFT correspondence. Don't worry about the letters. What it basically said was this: there's a mathematical connection between a universe with gravity inside it and a universe without gravity on its boundary. That might sound technical, but here's what it means for us in simple terms. Two completely different-looking theories, one living in 3D space with gravity and the other living in 2D space with no gravity, can actually describe the same reality, like two sides of the same cosmic coin. In one, we're floating in space. In the other, we're flat patterns on a distant screen, and both tell the same story. It's like reading a novel and watching its movie adaptation at the same time. Different formats, same plot, still sounds wild. It should. But here's the really interesting part. There's actual math behind this. The physics works. We can describe black holes, quantum fields, and even aspects of space-time using the holographic idea. It's not just philosophical, it's calculable. And it might help us solve one of the biggest puzzles in physics: reconciling quantum mechanics with general relativity. Because maybe the reason they clash is that we've been thinking about the universe in the wrong dimensions. Maybe the fundamental layer of reality is flatter than we thought. Now, you might be wondering, what does this mean for me? Well, nothing changes about your everyday life. Your body, your room, your dreams, they still feel 3D. You still walk through doors, not around them. But the holographic principle suggests that behind the scenes, reality might be playing out on a cosmic curtain. You're the star of your movie, but the film might be encoded on the edge of existence. And here's a soothing thought as you drift off. The universe, vast and mysterious, might be far simpler than we imagined. All its complexity, galaxies, thoughts, laughter, loss, could be compressed into a kind of cosmic code written on the boundary, projected inward, like a story told from the edge. And if that's true, then you, your thoughts, your dreams, might be part of a much bigger pattern, a quiet symmetry, a ripple in the grand hologram. Let it settle in your mind like a soft whisper. You're real, but maybe you're also a projection. Both can be true. And now, as your eyes grow heavy and your breath slows down, let that strange and beautiful idea rock you to sleep. You're floating in a universe that might just be a hologram. And somehow, that makes everything feel a little more magical. Good night, explorer. Renormalization. All right. Tonight we're heading into one of the strangest corners of physics. It's not flashy like black holes or time travel. It doesn't sound sci-fi, but it's deeply important. Because without it, the math behind our understanding of the universe completely falls apart. This quiet concept is called renormalization, and it's how physicists deal with the wild, untamed infinities that pop up when they try to make sense of particles and fields. You ready? Let's take this slow. Imagine you're making soup. You add some salt, taste it. A bit more salt. Taste again. Suddenly, too salty. Now imagine that you had a way to adjust the salt level after cooking, like retroactively tuning the ingredients to match the final taste. That's kind of what renormalization does for equations. It's how physicists adjust the flavor of their theories to match reality, especially when the math starts to go, well, infinite. Let's go back a bit. In the world of quantum field theory, the mathematical framework that describes particles like electrons and photons, things get messy. The theory says particles aren't just little dots flying around. They're ripples in fields, invisible vibrating fields that fill the entire universe. So when you look closely at a particle like an electron, you're not really seeing a tiny marble. You're seeing a disturbance, a wave, in a sea of energy. And here's the problem. When you try to calculate something simple, like how two electrons interact, your equations don't just give you a nice, neat answer. Instead, they give you infinity, over and over, like trying to add up every possible tiny interaction and discovering the sum is endlessly huge. It's like asking, how much does an electron weigh? And getting the answer, infinite kilograms. Clearly, something's off. This is where renormalization comes in. Instead of throwing the whole theory away, physicists found a way to clean up the math, to slice away the parts that go to infinity and keep the pieces that make sense. It works like this. First, you admit that your theory gives nonsense answers, unless you set some boundaries. So you say, okay, I'll assume the electron has a bare mass, something hidden underneath all the quantum fuzz. Then I'll add up all the messy stuff that happens around it, all the virtual particles, all the vacuum fluctuations, and I'll redefine the total. That redefinition, that's renormalization. You're not changing reality, you're just renaming the parameters in your theory so they match what you actually observe in experiments. It's like saying, I don't care what number the math gives me, I'll plug in a new number that makes the predictions come out right. To outsiders, it might sound like cheating, but it's not. Because renormalization isn't arbitrary, it's precise, it's consistent, and it works. It works really well. In fact, quantum electrodynamics, the theory of how light and matter interact, uses renormalization to make predictions that match experiment with mind-blowing accuracy. We're talking about results confirmed to 1 part in a billion. That level of precision doesn't happen by accident, and it goes beyond just fixing infinities. Renormalization taught physicists something deeper, that theories don't have to work at every scale to be useful. You don't need to know what happens at energy levels trillions of times higher than we can measure. You just need a theory that works here and now. It's like having a map that's only accurate within your neighborhood. It won't help you find a road in another country. But for your local walk, it's perfect. Renormalization let physicists create effective theories, models that are only meant to work within certain energy ranges. And that's okay, because sometimes being approximately right is all you need. Now you might be wondering, if it's so great, does it always work? Well, no, not all theories are renormalizable. Some fall apart no matter how hard you try to patch them. That's one of the big challenges in quantum gravity, trying to combine general relativity, which describes gravity, with quantum mechanics, which describes everything else. Gravity resists renormalization. It stubbornly spits out infinities that we can't clean up. That's why so many physicists are hunting for deeper theories, like string theory or loop quantum gravity, that might tame those infinities in new ways. But let's not get ahead of ourselves. Renormalization at its heart is a calming idea. It tells us, don't panic when the math gets messy. Step back, redefine what you mean by mass, or charge, or energy. Let the theory breathe. And you might find that, underneath all the noise, the universe still makes sense. So, tonight, as you drift off to sleep, think of renormalization like this. It's the art of turning chaos into clarity, the quiet magic that lets physicists pull meaning from the madness of quantum fields. It's not glamorous, but it's essential. And just like adjusting the seasoning in a good soup, it makes everything taste just right. Sleep tight, cosmic chef. CPT symmetry. Okay, let's play a game with reality. Imagine you're watching a video of someone dropping a glass of water. It slips from their hand, falls, and shatters on the floor. Now, hit rewind. The glass pieces lift up, reassemble in midair, and land perfectly back in their hand. Weird? Sure. But let's add one more twist. Let's say everything in that video also flips left to right, like you're seeing it in a mirror. And now, every particle becomes its opposite. Every electron becomes a positron. Every proton becomes an antiproton. Matter becomes antimatter. If after all that, rewinding time, flipping space, and switching matter with antimatter, the laws of physics still work exactly the same way. Congratulations, you've just experienced CPT symmetry. Sounds like a sci-fi puzzle, right? But it's real. It's one of the most profound symmetries in the universe. And tonight, as you relax and let your mind wander, we're going to unravel this elegant idea, gently. So, what does CPT actually stand for? C is for charge conjugation, swapping particles with their antiparticles. P is for parity, flipping spatial coordinates like looking into a mirror. T is for time reversal, running the universe backward. Each of these transformations on their own, they mess with things. They change how the universe behaves. But if you apply all three, C, P, and T together, something remarkable happens. The universe doesn't care. It behaves exactly the same. That's CPT symmetry. It's like a hidden rule baked into the very fabric of quantum field theory. A promise that no matter how strange things get, no matter how much you flip, rewind, or invert, physics still plays fair. Let's break it down. Start with charge conjugation. This is where you replace every particle with its antiparticle. So an electron with negative charge becomes a positron, which has positive charge. Quarks become antiquarks. Basically, matter becomes antimatter. Cool, right? But here's the thing. If you just do that one transformation, C, by itself, the universe doesn't always follow the same rules. Certain reactions don't behave the same when particles are swapped with their antiparticles. That's called C violation. Then there's parity, or mirror flipping. You've probably seen this in real life. Writing on a t-shirt gets reversed in the mirror. In physics, this means flipping the spatial coordinates, turning left into right and right into left. It turns out parity isn't sacred either. In the 1950s, scientists discovered that certain particles, like neutrinos, don't behave the same way in a mirror. That was shocking at the time. They expected the universe to be symmetric, but it wasn't. P-symmetry can be broken. And then there's time reversal, running the laws of physics backward. Throw a ball, watch it arc through the air, rewind the footage. It looks weird, but guess what? Many physical laws don't care which direction time flows. They're symmetric, but not all of them. Some reactions, especially in the world of subatomic particles, break time reversal symmetry. So here's the twist. Even though C, P, and T can each be broken on their own, when you combine all three, the universe balances out again. It's like a three-part lock. Turn one dial, it doesn't open. Turn two, still jammed. But line up all three and click. Perfect symmetry. This isn't just a nice idea. It's backed by serious math. In fact, the CPT theorem is one of the cornerstones of modern physics. It states that any Lorentz invariant quantum field theory, that is, any theory that respects the laws of special relativity, must obey CPT symmetry. It's not optional. It's built in. Think of it as the universe's ultimate reset rule, a quiet guarantee that no matter how strange things get, some underlying harmony remains. Now let's go deeper. What does CPT symmetry mean for us? Well, for one, it gives us confidence in our theories. If we ever found a process that truly violated CPT symmetry, it would mean something's fundamentally broken in our understanding of reality. That's huge. So far, we've never seen such a violation. The laws of physics seem to hold up their side of the bargain. But there's more. CPT symmetry connects to questions about time itself. If the universe truly obeys this symmetry, then reversing time, while also flipping charge in space, should lead to a universe that still makes sense. So, somewhere out there, maybe there's a mirror version of everything, a cosmic twin that plays in reverse. And in that reversed, mirrored antimatter universe, the rules are still consistent. It's a poetic thought. As you lie back, eyes growing heavier, let it settle in. The universe might be complex, unpredictable, full of chaos and chance, but beneath it all is something deeply stable, something symmetric, something quietly reassuring. CPT symmetry reminds us that nature has structure, that no matter how weird the quantum world gets, some rules are carved into the foundation. They don't bend, they don't break, they simply are. So sleep easy tonight. You're floating in a universe where time, space, and matter dance to a hidden rhythm, a symmetry that never forgets the balance. And that is kind of beautiful. Good night, thinker. The Casimir effect. So, picture this. You're in a room. Nothing's in it. No furniture, no light, no sound. Absolute stillness, complete vacuum. But is it really empty? Not according to quantum physics. Because in the strange logic of the quantum world, even the emptiest possible space, what physicists call the vacuum, isn't truly empty. It's buzzing, flickering, alive with activity. And one of the strangest ways we know this is through something called the Casimir effect. Let's start with the basics. In our everyday world, we think of a vacuum as nothing, a total absence of matter, no particles, no atoms, no energy, just blank space. But in quantum mechanics, even a vacuum isn't truly nothing. Instead, it's a sea of fleeting particles and antiparticles constantly popping into and out of existence. They appear for the briefest of moments, then annihilate each other and vanish. These are called vacuum fluctuations. Now here's where things get weird. In 1948, Dutch physicist Hendrik Casimir predicted a bizarre consequence of this quantum jitter. He imagined placing two uncharged, perfectly conducting metal plates very close together in a vacuum, just a few nanometers apart. What he found was that even in the absence of any heat, light, or electromagnetic fields, a force would arise between those plates, a tiny attractive force pulling them towards each other. But why? It has to do with the quantum fields that fill the vacuum. You see, even in empty space, quantum fields are never at rest. They vibrate with all possible frequencies, some high, some low. But when you introduce two closely spaced plates, something subtle happens. Not all those frequencies can fit between them. The space between the plates can only support certain wavelengths, those that fit the gap like a musical note fitting inside a flute. Outside the plates, there are more allowed wavelengths, more modes of vibration, so the vacuum fluctuations outside the plates are more intense than those between them. The result? A net pressure pushing the plates together. That's the Casimir effect, a force from nothing, or rather, from the restless energy of the quantum vacuum. And this isn't just theory, it's been measured. Physicists have observed this effect in laboratory settings using highly sensitive instruments. In fact, at nanoscales, it becomes a serious consideration in the design of tiny mechanical systems, like the microscopic machines inside electronics or quantum computing components. Now let's zoom out a bit and think about what this really means. The Casimir effect isn't just a curiosity. It's a window into the true nature of empty space. It tells us that vacuum isn't just the absence of stuff. It's a dynamic, fluctuating environment, a canvas painted with invisible energy. This also ties into the idea of zero-point energy, the lowest possible energy a quantum system can have, even when it seems like nothing's happening. In classical physics, if a system loses all energy, it just stops. But in quantum mechanics, even at absolute zero, particles still jitter, they still vibrate ever so slightly. So when we say vacuum, we're talking about the lowest energy state of a field, but never truly zero. The implications of this are huge. Some physicists believe that the energy of the vacuum might be tied to dark energy, the mysterious force driving the accelerated expansion of the universe. In theory, the vacuum energy should be massive, so massive, in fact, that it would tear the universe apart. But in practice, the observed vacuum energy is much smaller than what quantum field theory predicts. That mismatch between the theoretical and observed values is known as the cosmological constant problem, and it remains one of the biggest unsolved puzzles in modern physics. But back to the Casimir effect. One of the reasons it feels so profound is that it reveals how the universe reacts to boundaries. Place two plates in the void, and space responds. Reality changes. That subtle tug between the plates is the universe adjusting to new rules, new constraints. And this opens the door to even deeper questions. What happens if you change the shape of those boundaries? Could you engineer space itself to create different effects? Could we one day manipulate the vacuum to create propulsion, or even extract usable energy? These ideas are still speculative. But the Casimir effect proves that the vacuum is not inert. It's responsive. It has structure. And if we can learn to understand and manipulate that structure, who knows what might be possible? In some fringe theories, people have speculated about using Casimir-like effects to design exotic forms of propulsion, quantum sails, or ways of pushing against the vacuum itself. It sounds far-fetched, but the underlying idea is rooted in a real observable force. Another fascinating angle: some researchers are exploring how Casimir-like forces might affect biology on extremely small scales, like in the folding of proteins or the behavior of DNA strands in confined spaces. When you zoom in far enough, the rules of reality shift, and forces we ignore in daily life begin to play a powerful role. And philosophically, it's kind of humbling. We often think of the universe as mostly empty, just vast stretches of nothingness between stars. But quantum physics gently reminds us there is no true nothing. Even silence has a song. Even darkness has a flicker. Even emptiness holds energy. The Casimir effect is proof that the universe is never still, never silent. Even when you remove everything else, strip away light, matter, temperature, motion, something still remains. So when we say the plates are pushed together by nothing, what we're really saying is that space itself has an opinion. It responds to boundaries, to shapes, to the presence or absence of matter. And maybe in a way, so do we. We're shaped by invisible forces too, expectations, relationships, histories we don't fully understand. Sometimes it's the things we can't see that push us in one direction or another. Maybe the vacuum, like life, is more alive than it looks. And in the end, that's what makes the Casimir effect so magical. It's a quiet force, a whisper of the quantum world, a reminder that even the simplest scenarios, a couple of metal plates in a vacuum, can reveal profound truths about the nature of everything. All you need is a little curiosity and two plates placed very, very close together. Quantum tunneling. Imagine walking up to a wall. It's tall, it's solid, you can't climb it, you can't go around it. And if you try to walk through it, well, in the everyday world, you just bounce off. But in the quantum world, you might just appear on the other side. Welcome to the mind-bending world of quantum tunneling, where particles don't always play by the rules, and somehow, reality lets them get away with it. Tonight, as you unwind and relax, let's gently explore how this strange little phenomenon shapes everything from the sun to the possibility of your very existence. So what exactly is quantum tunneling? Let's picture a particle, say an electron. In classical physics, if the electron doesn't have enough energy to get over a barrier, it just stops. Like a skateboarder hitting a ramp that's too high, no way over. End of story. But in quantum mechanics, the rules are different. Particles don't behave like tiny marbles. They behave more like waves, fuzzy, spread out, uncertain. Their location isn't fixed until you measure it. It's described by something called a wave function, or a sort of probability map of where the particle might be. And here's the twist. That wave function doesn't just vanish when it hits a wall. It actually leaks into the barrier a little, like a soft glow. And if the barrier isn't too wide, that glow, the part of the wave function that survives, can emerge on the other side. And that means the particle has a small but real chance of appearing past the barrier, as if it had magically tunneled through a place it wasn't allowed to go. That's quantum tunneling. No digging, no shortcut, just vanishing on one side and reappearing on the other. Sounds impossible, right? But it happens constantly, all around you. And in fact, it's essential to life itself. Let's zoom out, way out, to the core of the sun. The sun shines because of fusion. That's when hydrogen nuclei, protons, smash together to form helium, releasing energy in the process. But here's the thing. Protons are positively charged. They repel each other. And even with the sun's intense heat, they technically don't have enough energy to overcome that repulsion and fuse. So how do they do it? Quantum tunneling. Even though the protons can't classically climb the energy barrier between them, their wave functions allow a chance, however small, that they'll tunnel through and get close enough to fuse. Without quantum tunneling, the sun would be dark, cold, lifeless. And if that doesn't make you pause, here's another thought. Quantum tunneling is also a core part of how modern technology works. Your smartphone, your laptop, the flash memory you use every day, they all rely on tunneling in tiny transistors and quantum dots. There's even a device called a tunnel diode that literally uses this effect to conduct electricity in special ways. Quantum tunneling is weird, but it's real. And it's not just useful, it's beautiful. Because it shows us that the world isn't always rigid, that even when something seems impossible, like a wall you can't climb or a dream that feels out of reach, there's still a small chance, a quiet loophole, a cosmic exception. Let's think about how this looks from a physics perspective. We describe barriers using potential energy, and we describe particles using wave functions. When the wave function reaches a barrier, it doesn't hit a hard stop. It fades, like fog meeting a window. But if the barrier is thin enough or low enough, Part of that wave makes it to the other side. The result? A tiny probability. But in a universe made of tiny particles doing this all the time, tiny probabilities add up to very real effects. Now you might be wondering, can we tunnel? Can a human suddenly appear on the other side of a wall? Technically, the math doesn't say it's impossible, but the chances, well, vanishingly small, like winning the lottery a billion times in a row, then doing it again the next second. So, no, don't try walking through walls just yet. But still, the idea is kind of romantic. That reality itself allows for magic, not the fake kind, but the kind that's built into the laws of nature. Quiet, subtle, mathematical. It's one of those rare places where the universe whispers, maybe. And tonight, as you drift off, think of all the little particles around you, tunneling, flickering, dancing with probability. They don't break the rules, they are the rules. And they remind us that sometimes getting to the other side isn't about force or power or speed. Sometimes it's about being patient, being still, letting the wave pass through. So close your eyes, picture the wall, and then gently imagine what's on the other side. The fine-tuning problem. Imagine walking into a room and finding a giant control panel, dozens of knobs, sliders, dials, each one labeled with a physical constant, the strength of gravity, the mass of the electron, the speed of light, the charge of the proton. And here's the weird thing. Every single setting is just right. Twist any knob just a little, up or down, and the universe as we know it stops working. Galaxies don't form, stars don't ignite, chemistry falls apart, life becomes impossible. This is the essence of the fine-tuning problem. It's the idea that the fundamental constants of nature, those deep underlying values baked into the laws of physics, seem to be perfectly calibrated for one extraordinary outcome, a universe that can support life. But why? That question sits at the intersection of science, philosophy, and even metaphysics. And tonight, we're going to explore it, gently, curiously, without rushing for answers. Let's begin with what we do know. The laws of physics include a set of constants, numbers that don't change no matter where or when you are in the universe, things like the gravitational constant, which controls the strength of gravity, the cosmological constant, which affects the expansion of space, the fine structure constant, which influences the strength of electromagnetic interactions, the masses of fundamental particles. None of these numbers are predicted by theory. They're measured. We just observe them and write them down. But the striking thing is this. If any of those numbers were just slightly different, the structure of the universe would unravel. For example, if gravity were just a tiny bit stronger, stars would burn too quickly. They'd collapse into black holes before life could evolve. If it were slightly weaker, stars might never ignite, just clouds of hydrogen floating in the dark. If the strong nuclear force were a bit stronger, protons would fuse too easily. The universe might be filled with helium and nothing else, no carbon, no life. If the electromagnetic force were slightly different, atoms wouldn't form stable molecules. Chemistry, the basis of biology, wouldn't work. This is the fine-tuning problem. Why are all these values in the narrow range that allows complexity, structure, and consciousness to emerge? It's not just one or two values, it's dozens, and their balance is incredibly delicate. Now, there are a few ways scientists and thinkers have tried to answer this. One is the anthropic principle. It says, well, of course the universe looks fine-tuned. If it weren't, we wouldn't be here to notice. We exist in a universe with life-friendly constants because those are the only kinds of universes where beings like us can arise and ask these questions. It's not a deep explanation, it's more of a selection effect. Like saying, of course I'm on Earth, not Pluto. Pluto doesn't support human life. It's true, but not necessarily satisfying. Then there's the multiverse hypothesis. This idea suggests that there isn't just one universe. There are countless universes, maybe even an infinite number, each with its own set of physical constants. In this vast cosmic lottery, Some universes have wild parameters and collapse instantly. Others drift cold and lifeless. But once in a while, one of them gets just right. Stars shine, atoms cling together, life evolves, consciousness awakens. That's our universe. Not because it's special, but because it's one of the rare ones where conditions are right. In this view, fine-tuning doesn't require a designer or a deep reason. It's just chance, filtered through the anthropic lens. But not everyone buys that. Some physicists think the fine-tuning might point to something deeper, maybe a yet undiscovered theory that makes the constants inevitable. Something more elegant, more fundamental, a theory of everything that reveals why these values couldn't have been otherwise. In other words, maybe the universe isn't fine-tuned. Maybe it's self-tuned. We just don't understand the mechanism yet. And of course, there are philosophical or theological interpretations too, arguments that fine-tuning suggests purpose or design, that the universe isn't random but intentional. Physics doesn't confirm or deny that. It simply observes, measures, builds, models. But the questions fine-tuning raises touch something deep in us, a sense of awe, of curiosity, of mystery. Let's bring this back down to Earth. Every breath you take is made possible by this cosmic balance. The air, the water, the sunlight. All of it is here because the physical laws aligned in a way that allowed atoms to form, stars to burn, planets to orbit, molecules to dance. It didn't have to be this way. Most possible universes wouldn't look like this, but ours does. And whether that's due to chance, necessity, or something beyond either, we may never fully know, but we can wonder. And maybe that's the point. The fine-tuning problem isn't just about numbers, it's about context, about stepping back from our daily routines to see the sheer improbability of it all, that the constants are just right, that the forces balance, that the universe unfolds in a way that gives rise to stars and minds and the ability to ask, why? So when you look up at the night sky, remember, you're not just seeing stars. You're seeing the outcome of a perfectly calibrated system written into the fabric of space itself. Whether by randomness, necessity, or something else entirely, the universe is tuned for structure, for order, for awareness. And maybe that's the most beautiful puzzle of all. Gauge symmetry. If you've ever looked at a perfectly balanced snowflake or a spiraling galaxy and felt there was some kind of harmony, some quiet, invisible order, then you've already brushed up against the core idea behind gauge symmetry. It's one of the most elegant, powerful, and foundational principles in all of physics. A quiet rule book the universe seems to follow, but it's also subtle, hidden, like the deep grammar behind the language of reality. So let's begin at the beginning. In physics, a symmetry isn't just something that looks the same on both sides. It's a kind of invariance, a rule that says, even if you change something about a system, the underlying laws remain unchanged. For example, imagine spinning a perfect sphere. From any angle, it looks the same. That's rotational symmetry. Or imagine moving your entire experiment a few feet to the left. If nothing changes in the results, you've got translational symmetry. Now, gauge symmetry is something deeper. It's not about the symmetry of shapes in space, but about the symmetry of the fields that govern particles, the invisible forces that fill the universe. To understand this, we need to talk about fields. In modern physics, particles aren't little dots zipping through space. They're excitations, little ripples, in invisible fields. There is an electromagnetic field for electricity and magnetism, a Higgs field that gives particles mass, and many more. And just like a sea can have waves that look different but still obey the same physics, these fields can transform in subtle ways without changing the outcome. That's gauge symmetry. It says you can tweak how you describe the field locally, right here, right now, and as long as you do it consistently, the physics stays the same. This may sound abstract, but it's the backbone of our best physical theories. Let's take the electromagnetic field. It's described by quantum electrodynamics, or QED. The gauge symmetry here is called U1 symmetry. In simple terms, this symmetry allows you to shift the phase of the electron field, like turning the dial on a wave's position, without changing any physical results. But here's the twist. When you demand that this symmetry holds everywhere, it forces the existence of the electromagnetic field. That is, gauge symmetry gives rise to the force itself. This pattern repeats in other forces too. The weak nuclear force, gauge symmetry. The strong nuclear force, gauge symmetry. Even attempts to unify gravity into this framework revolve around extending gauge symmetries into new domains. In fact, the standard model of particle physics, our best theory of how particles and forces interact, is built entirely out of gauge symmetries, every particle, every force, all arising from the requirement that certain transformations leave the laws unchanged. This isn't just mathematical beauty, it's predictive power. Gauge symmetry tells us which particles exist. It tells us how they interact. It tells us which forces are allowed. It's like discovering that grammar doesn't just describe language, it creates it. And it gets even deeper. In 1918, the brilliant mathematician Noether proved something astonishing. Every symmetry in nature corresponds to a conserved quantity. If a system is symmetric under time translation, then energy is conserved. If it's symmetric under rotation, then angular momentum is conserved. And when you apply this to gauge symmetry, you get the conservation of charge. In other words, the reason electric charge doesn't just vanish or change over time is because the equations describing the fields are invariant under local phase shifts. That's mind-blowing. It means conservation laws, those deep, reliable truths we depend on, are just shadows of symmetry. Now, why is it called gauge symmetry? The term comes from early work in electromagnetism, where the potentials that describe electric and magnetic fields could be gauged or shifted without changing physical results. As theories evolved, physicists discovered that these gauge freedoms weren't just artifacts of our math. They were telling us something fundamental about the structure of the universe. It's as if nature doesn't care how you describe something, only that you do it consistently. So why does this matter? Because gauge symmetry doesn't just help us write elegant equations, it shapes reality. It dictates what forces can exist. It determines which particles can interact. It constrains the possible forms of matter and energy. And it offers hints about what lies beyond our current understanding. Physicists searching for a grand unified theory, a framework that unites all forces, are really searching for deeper, more comprehensive gauge symmetries. Bigger groups, more transformations, a grander version of the same principle that ties electromagnetism to light, quarks to gluons, and the Higgs field to mass. Even string theory at its core is about symmetry, about describing reality in ways that preserve certain transformations no matter how you twist or compactify the dimensions. And in the real world, gauge symmetry governs the interactions in your phone, in your body, in the stars above. Every time light hits your eye or an atom binds to another atom, you're witnessing the consequences of invisible symmetries that have been humming through the universe since the beginning. Gauge symmetry is quiet, elegant, invisible to the eye, but essential to the machinery of existence. It's the language behind the laws, the pattern beneath the particles, the symmetry that doesn't just describe the universe, it shapes it. And that, in the end, is what makes it so powerful. Vacuum fluctuations. So, take a moment and imagine the quietest place possible. No air, no light, no particles, no temperature, just nothing. Total emptiness. But here's the twist. According to quantum physics, even that perfect nothingness isn't truly empty. In fact, it's teeming with activity, with energy, with particles popping in and out of existence like flickers of thought in a sleeping mind. This isn't science fiction. It's one of the weirdest, most beautiful facts in quantum field theory. It's called a vacuum fluctuation. Let's slow that down. In classical physics, a vacuum is nothing, no matter, no radiation, no movement. But in quantum physics, the vacuum is not zero. It's not still. It's not dead. Because even in its lowest energy state, a quantum field still jitters. It vibrates. It fluctuates. Why? Because of something called the Heisenberg uncertainty principle. It tells us that you can't know both the energy and the time of a system with perfect precision. The shorter the time scale, the fuzzier the energy. That means that for tiny blips of time, energy can rise from zero, just a little, just enough to create a pair of virtual particles, a particle and its antiparticle. They appear, interact, and vanish again, too fast for us to directly observe. But they're there. These fleeting phenomena are vacuum fluctuations. They're not stable. They don't last. But they leave an imprint, a signature. And we can measure their effects. For instance, remember the Casimir effect? Two metal plates placed close together in a vacuum feel a tiny force pulling them together. That's because the space between the plates restricts the vacuum fluctuations compared to the space outside. So even though the plates sit in nothing, they still feel the tug of the quantum vacuum. Another powerful example, the Lamb shift. This is a tiny shift in the energy levels of hydrogen atoms, so small it was only discovered through extremely precise experiments. The shift occurs because vacuum fluctuations constantly nudge the electron, jostling it ever so slightly out of position. These aren't abstract theories, these are measured effects. And they're all caused by fluctuations in what we used to think was emptiness. Even more incredibly, vacuum fluctuations may play a role in the structure of space-time itself. In quantum field theory, every field, electromagnetic, Higgs, strong nuclear, has a ground state or vacuum. But that vacuum isn't flat. It has texture, energy, potential. It can influence gravity, warp space, affect time, and some physicists believe that fluctuations in this vacuum energy, multiplied across all of space, might be responsible for the mysterious dark energy that's causing the universe to expand faster and faster. That's right, the runaway acceleration of cosmic expansion might be the result of the vacuum not being perfectly quiet. But here's where things get weird. When physicists try to calculate the energy of the quantum vacuum, the numbers are huge, enormous, like 120 times bigger than what we observe in reality. This massive mismatch between theory and measurement is known as the cosmological constant problem. It's one of the biggest unsolved puzzles in physics. Why does the vacuum have energy at all? And if it does, why isn't it tearing the universe apart? There are no clear answers, just clues and lots of questions. Now, take a step back. Vacuum fluctuations challenge our basic intuition about nothingness. They show us that absence is not absence, that stillness is not still, that even when everything has been stripped away, reality hums with invisible motion. These fluctuations also play a crucial role in quantum field theory. In particle physics, interactions aren't direct collisions. They're more like disturbances, rippling through quantum fields, with virtual particles popping in and out along the way. Every force, every exchange, every bit of matter is affected by these vacuum processes. They even affect the mass of particles. The Higgs field, for example, provides mass to particles through constant interaction. But vacuum fluctuations modify that mass slightly, like static on a clean signal. And here's a deeper philosophical idea. If vacuum fluctuations are always happening, always shifting the quantum soup of fields beneath our reality, then the universe isn't just dynamic on the surface. It's dynamic underneath, at its very core. What we call emptiness is actually a foundation of endless possibility, a field of potential, constantly generating blips of matter and antimatter, borrowing energy from nothing, paying it back in fractions of a second, and quietly shaping the cosmos as it does. Some theories even suggest that entire universes might be born from quantum fluctuations. In the inflationary model of cosmology, tiny fluctuations in the early universe, caused by vacuum energy, could have seeded the large-scale structure we see today. Galaxies, clusters, filaments of matter stretching across the sky. A ripple in the vacuum could, over billions of years, become a star, a planet, a mind. So when we talk about vacuum fluctuations, we're not talking about trivia. We're talking about the subtle heartbeat of reality, the ever-present hum of the quantum fields that make up everything we know. It's not empty, it's not quiet, it's the beginning. Quantum gravity. There's a fracture running through the foundations of modern physics. On one side, general relativity. Einstein's theory of gravity, smooth, geometric, majestic. It describes how planets orbit stars, how time bends near black holes, and how space itself curves under the weight of mass. On the other side, quantum mechanics, the theory of the very small, wild, jittery, probabilistic. It governs atoms, particles, fields, and the strange rules that come with them. Both theories are spectacularly successful. Both have been confirmed by countless experiments. But here's the problem. They don't get along. You can't just plug gravity into quantum mechanics or vice versa. The math breaks. Predictions go infinite. Equations collapse. And that's where quantum gravity comes in. It's the effort to unify the large and the small, to find a theory that can describe the force of gravity using the same quantum language that describes electrons, photons, and quarks. Let's break this down. General relativity tells us that gravity isn't really a force at all. It's the bending of space-time itself. Massive objects curve the fabric of reality, and other objects follow those curves. That's why Earth orbits the Sun, or why light bends near a black hole. But in quantum physics, everything is a particle or a field. Forces come from particles, like the photon for electromagnetism or the gluon for the strong nuclear force. So what about gravity? If gravity is a force, should it have a particle too? In theory, yes. Physicists call it the graviton, a hypothetical massless particle that mediates gravitational interactions. If it exists, it would carry the smallest possible chunk of gravity, just like photons carry light. But we've never detected a graviton, not directly. Gravity is just too weak compared to other forces, and gravitons, if they exist, would be extremely hard to observe. Still, the idea of a graviton is part of the broader goal, to quantize gravity, to describe space-time not as a smooth fabric, but as something granular, fluctuating, uncertain, at the smallest scales, just like everything else in quantum mechanics. And here's where things get interesting. At a certain scale, called the Planck scale, quantum effects become so strong that our smooth picture of space-time breaks down. Distances as small as 1035 meters, times as short as 1043 seconds. At that scale, the concepts of space and time may not even make sense anymore. Instead of smooth curves, space-time might be a frothy, turbulent mess, constantly bubbling with quantum fluctuations, a foam of many black holes, wormholes, or tangled strings of energy. This is the quantum gravity regime. We're not there yet experimentally. We don't have telescopes or colliders powerful enough to probe those distances. But theoretically, it's a frontier many physicists are trying to explore. One of the most famous approaches is string theory. In string theory, particles aren't points. They're tiny vibrating strings. Different vibrations create different particles. Gravity? It emerges naturally as one of those vibrational modes, the graviton. String theory also brings extra dimensions, not just the four we know, 3 of space, 1 of time, but up to 10 or 11 dimensions, curled up so tightly we don't see them. The math is beautiful, but it's also complex, and we haven't yet found experimental proof that string theory is the right path. Another major approach is loop quantum gravity. It doesn't rely on extra dimensions or strings. Instead, it tries to quantize space-time itself. In this view, space is made of tiny loops, discrete bits of geometry woven into a network. It's like zooming in on a fabric and seeing it's made of threads. This leads to the idea that space and time are not continuous but quantized. made of smallest possible units. No smaller, no smoother. Loop quantum gravity has made some intriguing predictions, especially about black holes and the early universe, but like string theory, it's still awaiting experimental evidence. There are other approaches too: asymptotic, safety, causal dynamical triangulations, emergent gravity, each with its own view of what quantum gravity should look like. But here's what they all share. They try to solve the tension between general relativity and quantum mechanics. They seek a picture where gravity and the other forces emerge from a single, unified framework. And why is that so important? Because without quantum gravity, we can't fully understand black holes. We can't understand the Big Bang. We can't understand what happens when space-time reaches its limits, its edges, where curvature becomes infinite and the classical laws break. Take black holes, for example. General relativity says they have a singularity at their center, an infinitely dense point. But quantum mechanics doesn't allow true infinities. Something else must be happening at the heart of a black hole, something quantum. Or consider the birth of the universe. At time zero, during the Big Bang, our equations break down. Space and time seem to emerge from something. But what? Only a theory of quantum gravity could tell us. And even more tantalizing, quantum gravity might help us understand if space-time is fundamental, or if it's just an emergent property, like temperature or pressure arising from deeper, microscopic rules. Some physicists believe space-time might come from entanglement. That geometry is an illusion, that reality, at its deepest level, is made not of space or time, but of relationships, connections, quantum information. In this view, the universe is not a container, it's a web. And gravity, it's just the shape that web takes when you zoom out. That's quantum gravity, not just a merger of equations, but a reimagining of what reality is. We're not there yet. But every year we get closer, with new ideas, with better math, with deeper insight. And one day, maybe through the flicker of a black hole or the whisper of ancient light, we might finally hear the voice of space-time itself. The anthropic principle. Let's start with a question that feels almost too big to ask. Why does the universe seem perfectly set up for life? Not just for matter to exist, but for stars to shine, planets to form, chemistry to work, and eventually for conscious beings to emerge and look around. Out of all the ways the laws of physics could have worked, why do they work this way? Why this universe? And not some silent, lifeless void. This is where we meet one of the most controversial and thought-provoking ideas in modern science and philosophy, the anthropic principle. At its heart, the anthropic principle is very simple. It says, we observe the universe the way it is, because we are here to observe it. It sounds obvious, maybe even circular, but let's slow down and unpack what that really means. Start with this. The constants of nature are extremely specific. If gravity were slightly stronger or weaker, stars might never form. If the strong nuclear force were just a little off, atoms wouldn't hold together. If the electromagnetic force were different, chemistry would collapse. No molecules, no DNA, no us. Even the rate of expansion of the universe had to be just right. Too fast, and matter would never clump together. Too slow, and the universe would have collapsed back in on itself before anything could evolve. It's like walking into a room and seeing 100 dials on a wall, all perfectly tuned. The temperature, the oxygen level, the lighting, the pressure, all exactly what's needed to support life. It makes you pause, makes you wonder, is it coincidence? That's what the anthropic principle tries to address. There are two main versions. First, the weak anthropic principle. This is the modest version. It says that the universe must have properties compatible with our existence, because we exist. In other words, it's not surprising to find ourselves in a life-permitting universe, because we couldn't exist in a universe that doesn't permit life. It's like being on Earth and saying, of course I'm not on Jupiter, it's not habitable. That's true, but it doesn't tell you why Earth is habitable in the first place. Then there's the strong anthropic principle, which goes further. It suggests that the universe must allow for conscious life, that life isn't just an accident, but a necessary part of the structure of the cosmos. This version is more philosophical and more controversial. It raises deep questions about design, purpose, and even consciousness itself. But there's another twist. Some scientists think the anthropic principle is best explained by the multiverse. According to this view, there isn't just one universe, there are countless ones, each with different physical constants, different rules, different outcomes. Most of those universes are barren, empty, chaotic. But a few, by sheer probability, have the right conditions for life. And we happen to live in one of them. Not because it was made for us, but because in all the vast randomness, some universes had to be right. We're here, in one of those rare places, simply because this is the only kind of universe where anyone can be. This idea reframes the anthropic principle. Instead of asking, why is the universe fine-tuned for us, it becomes, out of all the possible universes, we had to end up in one where life is possible. But not everyone agrees. Some physicists think the anthropic principle is too vague, that it's a placeholder, not an answer. That instead of accepting fine-tuning, we should be looking for a deeper theory that explains why the constants are what they are. Maybe the values aren't random at all. Maybe they're necessary. Maybe there's a deeper symmetry we haven't discovered yet, something that locks these numbers into place with no wiggle room. Or maybe it's something else entirely. The anthropic principle also opens up fascinating questions about consciousness. If the universe is structured in such a way that observers can arise, does that say something about the nature of observers? Is consciousness just an accidental outcome of physical laws? Or is it somehow fundamental? Some interpretations of quantum mechanics, like the participatory anthropic principle, suggest that observers play a role in shaping reality. That without observation, there is no definitive universe, no collapsed wave function, no is. That's not proven, it's speculative, but it shows just how far the anthropic principle can stretch, from cosmology to consciousness, from physics to philosophy. It's an invitation to ask the big questions. Why this universe? Why these laws? Why life? Why us? And maybe there's no single answer. Maybe the anthropic principle isn't a solution but a perspective, a way to remind us that the universe isn't just a cold, random machine, but a place that, against all odds, gave rise to minds that can ask questions, tell stories, and wonder why things are the way they are. That's the strange beauty of it all. We are part of the universe. Yet we're also observers of it. We are shaped by its laws. And yet we reflect on them. Built from atoms, yet somehow aware of the atoms we're made of. Maybe the universe is fine-tuned. Maybe it's just one lucky draw in an infinite multiverse. Or maybe it's all still waiting to be understood. The Wheeler-DeWitt equation. Most equations in physics describe how things change over time. Newton's laws predict how an object moves from one moment to the next. Schrödinger's equation describes how a quantum system evolves. Even Einstein's field equations tell us how space-time bends as things move and shift. But then, there's one equation that breaks that pattern entirely. One that doesn't talk about time. One that seems to freeze the universe into a single timeless snapshot. It's called the Wheeler-DeWitt equation, and it might be one of the most mysterious pieces of math in all of theoretical physics. Let's take it from the top. This equation was developed in the 1960s by physicists John Wheeler and Bryce DeWitt. Their goal? To merge the principles of general relativity, Einstein's geometric theory of gravity, with the strange probabilistic rules of quantum mechanics. In short, they were looking for a way to quantize gravity. Now, in quantum mechanics, we usually deal with a wave function, a kind of mathematical object that describes all possible states of a system. When applied to particles, this wave function evolves over time, usually according to Schrödinger's equation. But when Wheeler and DeWitt applied the same logic to the entire universe, something strange happened. The equation they got had no time variable, no ticking clock, no before and after, just one enormous wave function that described all possible configurations of the universe at once. This is the Wheeler-DeWitt equation. It's a kind of master wave function, not for an atom, not for a particle, but for everything: space, geometry, energy, matter, curvature. It treats the entire universe as a quantum object. And time? It doesn't appear. This leads to something called the problem of time in quantum gravity. In trying to combine general relativity and quantum mechanics, we discover that time, the very thing we rely on to describe motion, memory, change, simply vanishes from the math. So what does that mean? Are we wrong about time? Is it an illusion? Is the universe actually timeless, and time only emerges as an approximation, something that arises when you zoom in on part of the universe, like the ticking of a clock in the middle of a still forest? Some interpretations suggest exactly that time isn't a fundamental part of reality. Instead, it emerges from deeper relationships: entanglement, correlation, complexity. In this view, what we experience as the flow of time is just the unfolding of entangled quantum information within a universe that, on the deepest level, doesn't change at all. It's like watching a movie. The film is already there, every frame already written, but we experience the illusion of time by watching the frames in sequence. We think things are moving forward, but in a sense they're already there. The Wheeler-DeWitt equation supports this radical idea. It suggests that the entire history of the universe, from the Big Bang to today to whatever comes next, is encoded in a single timeless object, the wave function of the universe. And yet, within that static picture, observers like us can emerge with our memories, our clocks, our questions. Physicist Carlo Rovelli describes this as relational time. Time isn't an independent thing flowing through space. It's something that arises from relationships between things, between observers, between parts of the wave function. This might sound abstract, but it's not just philosophy. It has consequences. If time is not fundamental, it changes how we think about causality, about thermodynamics, about the beginning and end of the universe. It also influences our understanding of quantum cosmology, the study of the universe at its most fundamental level. Using the Wheeler-DeWitt equation, researchers try to model the birth of the universe not as a moment in time, but as a kind of quantum transition between different configurations of space. Some solutions to the equation describe universes that bounce into existence, contracting, reaching a minimum size, then expanding again. Others suggest our universe might be just one branch of a larger, timeless multiverse. And yes, the math is hard, it's speculative, but it's also deeply beautiful, because it asks us to question one of the most basic assumptions we hold, that time is real. Imagine a universe where everything that ever happened, and everything that ever will, simply exists, not stretched along a timeline, but coexisting in one giant interwoven structure. In that picture, the past isn't behind us. The future isn't ahead. Everything just is. And we, moving through it, are like waves rising and falling in a sea that was always there. That's the world the Wheeler-DeWitt equation describes. It's strange, it's humbling, and it's still not fully understood, but it might be our best clue yet into the true nature of space, time, and everything we call reality. Noether's theorem. At first glance, the universe feels wild, dynamic, full of unpredictable motion. Planets spin, particles collide, galaxies swirl, atoms vibrate. But underneath all of that chaos lies symmetry, quiet, powerful symmetry. And thanks to one brilliant idea, we now know that every symmetry in nature is tied to a law of conservation. This idea is known as Noether's theorem, and it might be one of the most important and beautiful concepts in all of theoretical physics. Let's begin with the person behind it, Emmy Noether. In the early 20th century, at a time when women were often excluded from academic institutions, Noether quietly revolutionized the foundation of physics. Her work didn't just solve a mathematical problem, it rewrote how we understand the laws of nature. So what did she do? She proved that for every continuous symmetry in the laws of physics, there's a corresponding conserved quantity. Let's break that down. Start with symmetry. In physics, a symmetry doesn't necessarily mean something looks pretty or mirrored. It means the laws of physics don't change under certain transformations. For example, imagine you do an experiment in your lab on Monday. You do the same experiment on Tuesday. If the results are the same, we say physics is invariant under time translation. That's a symmetry. Noether's theorem says, because the laws don't change over time, energy is conserved. Move your experiment to a different location. If the results are the same, physics is invariant under spatial translation. And Noether's theorem tells us that leads to the conservation of linear momentum. Rotate your experiment in space. Same laws, same results. That symmetry leads to the conservation of angular momentum. Time symmetry, energy conservation. Space symmetry, momentum conservation. Rotational symmetry, angular momentum conservation. This isn't just coincidence. It's a fundamental truth about how nature works. And it means something profound. Conservation laws aren't arbitrary. They're the result of symmetry. Let that sink in. The fact that energy doesn't just disappear, that momentum is preserved in a collision, that angular momentum stays constant in a spinning planet. Those aren't just experimental observations. They're the mathematical consequences of symmetry. Noether's theorem bridges two worlds, the abstract realm of geometry and the concrete world of physical law. It's a translation key, a way of taking the deep patterns of symmetry and turning them into something real and measurable. And the beauty of it? It works across all of physics. In classical mechanics, in quantum field theory, in general relativity, Noether's theorem holds. Even in particle physics, where gauge symmetries underlie the standard model, Noether's theorem is quietly at work, ensuring conservation of charge and other quantities. For instance, the conservation of electric charge emerges from a symmetry known as U1 gauge symmetry. That's Noether's theorem in action. Which I titled again. The idea is so powerful, it has even helped physicists rule out impossible theories. If a proposed model breaks certain symmetries, and thus would break conservation laws, it likely doesn't describe our universe. And it's not just about conservation laws, it's about understanding why the laws exist in the first place. Without Noether's insight, energy conservation might seem like a convenient fact of nature. With her theorem, we know it's a result of the universe not caring when something happens. A reflection of time symmetry. It's a quiet, almost philosophical realization. That the universe's deepest truths aren't enforced by external rules, but by its own internal harmony. The laws of nature are self-consistent, balanced, elegant, and Noether's theorem reveals that balance. Even modern cosmology, which deals with the expanding universe, has to wrestle with Noether's ideas. Because when time symmetry is broken, as it is in an accelerating universe, energy conservation becomes more complicated. That's not a flaw in Noether's theorem. It's a signal, a clue, a way of interpreting how the universe is changing. So what does all this mean for you? It means that every time you toss a ball or watch a comet streak across the sky or see a turbine spin, you're witnessing the quiet fingerprint of symmetry. It means that motion, energy, and dynamics, all the things that give the universe its rhythm, are rooted in something still, something unchanging, something symmetric. And it means that the universe doesn't just behave logically, it behaves beautifully. All thanks to Emmy Noether, who saw beneath the surface and revealed that the laws of physics are a reflection of invariance. Symmetry isn't just a pattern, it's a principle, and from it, all conservation flows. Quantum entanglement, advanced perspective. By now you've probably heard the term quantum entanglement. Two particles become connected in such a way that measuring one instantly tells you something about the other, even if they're light years apart. It's weird. It's often described as spooky action at a distance, and it's one of the most famous and misunderstood ideas in physics. But what's really happening? Let's go deeper, past the pop science version, into the strange, tangled core of this quantum phenomenon. Because entanglement isn't just a party trick. It's not just about instant communication or science fiction teleportation. It's a feature of reality that challenges everything we think we know about space, information, and separateness. So, let's start with the basics just to set the stage. Imagine you have two particles, say electrons. You put them in a special interaction, and they become entangled. This means their quantum states are no longer separate. Instead of having two independent wave functions, they now share one combined wave function. That wave function describes the whole system, not the parts. So now when you measure one electron, say its spin, you instantly know the spin of the other, no matter how far away it is. But that's the surface level view. The deeper truth is this: entangled particles don't have their own properties until they're measured. It's not that they have hidden states waiting to be revealed. It's that those states literally don't exist as separate facts until a measurement happens. The system as a whole has well-defined correlations, but the individual parts? They're undefined until observed. That's the essence of quantum non-separability, and it violates everything classical physics assumes. In the classical world, you can describe a system by describing its parts. Take a car apart, understand each piece, and you can understand the whole. In the quantum world, entangled systems can't be reduced to their components. The whole is fundamentally more than the sum of its parts. That's why entanglement is sometimes called the glue of quantum mechanics. And the implications are enormous. Let's talk measurement. And when you measure one particle in an entangled pair, you collapse the entire shared wave function. But how does the other particle know? It doesn't. There's no signal sent, no hidden message. What happens is that your measurement creates a new boundary between quantum potential and observed outcome. The results are correlated because they were never separate to begin with. And that's the uncomfortable truth. Quantum entanglement breaks the idea of local realism. It says the world is not built from little billiard balls with fixed properties. It's built from relationships, abstract mathematical objects that don't fit inside our everyday understanding of space and time. In some interpretations, like the many worlds interpretation, every possible measurement outcome actually happens in different branches of the universe. So when you measure one particle and find a result, you're also branching into a version of reality where that outcome exists, and the entangled partner follows that branching path with you. In other interpretations, like relational quantum mechanics, the properties of quantum systems aren't absolute at all. They're relative to the observer. What's true for one observer might not be for another. Entanglement becomes a story about context. But here's where things really stretch your mind. Entanglement isn't just between two particles. You can entangle 3 or 4 or millions. And once that happens, the structure becomes more like a web, a lattice of information where each piece is tied to others in a vast, complex geometry. Physicists have found that the amount of entanglement between particles can be used to calculate things like entropy, information, even geometry. There is a growing idea that space itself might emerge from entanglement, that the smooth fabric of space-time, the grid we move through, is built from quantum entanglement on a deeper level. This isn't just a metaphor, it's a mathematical possibility. In certain models from string theory and quantum gravity, the entanglement structure of a quantum system determines the shape of the space it lives in. In other words, entanglement might build the universe. This leads us to holography, the AD-S-CFT correspondence, and the idea that a lower-dimensional quantum field theory, full of entanglement, might create the illusion of higher-dimensional space. It's abstract, complex, and still developing. But what we know for sure is this. Quantum entanglement is not just about particles being connected. It's about the deepest structure of reality, being inherently non-local, relational, and fundamentally stranger than anything classical physics imagined. And we've barely scratched the surface. Entanglement is being used in quantum computing, where qubits rely on entanglement to perform parallel computations. It powers quantum encryption, where entangled particles reveal eavesdroppers instantly. It plays a role in quantum teleportation, where the state of a particle can be transmitted perfectly, but indirectly, from one place to another using entanglement and classical information. And the more we study it, the more it seems like entanglement isn't an exotic effect. It's the rule. A rule that tells us we've been thinking about the universe all wrong, that space and separateness, distance and independence might all be illusions, and that maybe everything really is connected, not by strings, not by magic, but by math, by wave functions, by entanglement. The black hole information paradox. Black holes are mysterious, massive, silent, inescapable. They swallow everything, matter, light, time itself, and nothing is supposed to return. But in the 1970s, something unexpected happened. Stephen Hawking discovered that black holes aren't entirely black. Thanks to quantum effects near the event horizon, they emit radiation, Hawking radiation, and over time that radiation causes a black hole to evaporate. Eventually, it disappears, which leads to a problem, a big one. Because if a black hole vanishes and nothing escapes from it, not even information, then the information about what fell in is gone forever. But in quantum mechanics, information can't be destroyed. This contradiction is known as the black hole information paradox. Let's slow down and unpack it. In classical general relativity, a black hole is defined by just a few properties: mass, charge, and spin. No matter what falls in, stars, books, ice cream cones, it all gets compressed into a singularity, and the black hole's exterior reveals nothing about the details. This idea is summed up in the phrase, "Black holes have no hair." But quantum mechanics says something different. It insists that information is conserved. If you know the wave function of a system at one moment, you should be able to recover it at any later time. This principle, unitarity, is at the core of quantum theory. So what happens when something falls into a black hole? If the black hole radiates and disappears, where did the information go? If it's lost, then quantum mechanics breaks. If it's preserved, then how? Hawking's original calculation suggested that black hole radiation is purely thermal, random, unstructured. That means it carries no information about what fell in. And if that's true, then all that information is lost as the black hole evaporates. But that violates unitarity. So began decades of debate. Physicists were divided. Some argued that we'd need to modify quantum theory. Others said that general relativity must break down near black holes. And others still believed that the paradox would vanish once we fully understood quantum gravity. In the 1990s, new ideas started to emerge. One of the most important was the holographic principle, the idea that all the information contained in a volume of space can be described by data on its boundary. This principle was supported by string theory and the ADS-CFT correspondence, which showed that black holes could be described in a lower-dimensional quantum theory without gravity. In this framework, the information wasn't lost. It was encoded on the event horizon, like a cosmic hard drive. Hawking himself eventually revised his position, proposing that black holes might store information on their surface in subtle quantum ways. But that led to even more questions. If information is preserved, how does it get out? Hawking radiation appears to be random, but if it carries information, then it must somehow encode the entire history of what fell into the black hole. That's like trying to reconstruct a book from the glow of a dying ember. Some physicists suggest that information is slowly leaked out, bit by bit, during the black hole's lifetime. a process that would make Hawking radiation non-thermal in the later stages. Others think information escapes only at the very end, during the final quantum death of the black hole. And then came the firewall paradox. In 2012, a group of physicists proposed that if information escapes from a black hole, the event horizon might not be smooth as general relativity predicts, but instead a searing wall of high-energy particles. A firewall. This violates the idea that falling into a black hole should feel normal, at least until you hit the singularity. So now we're stuck. Keep the smooth horizon, you might lose information. Keep the information, you might get a firewall. Different interpretations try to solve this in different ways. Fuzzball theory from string theory suggests black holes are just tangled strings. No singularity, no horizon, and no paradox. ER=EPR proposes that entangled particles are connected by wormholes, which could act as channels for information to escape. Complementarity says that what one observer sees outside the black hole may be different from what another sees falling in, and both are valid. But none of these answers are final. We still don't fully know how information escapes, or whether our understanding of space, time, or reality itself needs to change. What we do know is this. The black hole information paradox is not just about black holes. It's about the limits of our laws. Where quantum theory and gravity meet, something has to give. And when we finally solve this paradox, we might discover a new framework, a new foundation, one that explains not just how black holes work, but how everything works. Tachyonic particles. In the world of relativity, one rule stands tall. Nothing can travel faster than light. It's a cosmic speed limit, unbreakable, absolute. But what if, just what if, some particles are already beyond it, not by breaking the limit, but by never being under it in the first place? Welcome to the strange world of tachyons, hypothetical particles that always move faster than light. Let's take a step back. In Einstein's theory of special relativity, the speed of light is a barrier. Particles with mass can get close to it, but never reach or exceed it. Doing so would require infinite energy. Light speed is not just a fast pace, it's a wall. But relativity also leaves room, mathematically, for a different kind of particle, one that's not just fast, but fundamentally superluminal. These are called tachyons, from the Greek tachy, meaning swift. Tachyons are not particles that speed up past light. That's impossible. Instead, they would be particles that always travel faster than light. In fact, they could never slow down to the speed of light, just as normal particles can never speed up to it. It's like being born on the other side of a mirror. But this idea causes problems, because according to special relativity, faster-than-light particles would violate causality. That means events could happen out of order. Effects could precede causes. You could, in theory, send a message into your own past. The timeline would unravel. Paradoxes would pile up. And yet, the math doesn't forbid them outright. In quantum field theory, tachyons sometimes show up, not as real particles, but as indicators that something is unstable. A tachyonic mass in a field doesn't mean particles are zooming faster than light. It usually means the field is in the wrong configuration, like a ball sitting at the top of a hill instead of in a valley. The classic example? The Higgs field. Before symmetry breaking, the Higgs field had a tachyonic mass term. That didn't mean faster than light Higgs particles. It meant the field was unstable, and it rolled down into a stable vacuum. Once it settled, the symmetry broke, particles gained mass, and the tachyon disappeared from the equations. So in that sense, tachyons may not be real particles, but mathematical signs of instability. Still, they're intriguing. Some versions of string theory used tachyons to explore different vacuum states. Others used tachyon condensation to describe phase transitions in the early universe. And while we've never observed a tachyon directly, the idea keeps popping up because it challenges our assumptions. It asks us, What if reality isn't limited by light speed? What if there's a whole layer of the universe that lies beyond the speed of light, perpetually out of reach but still influencing the structure of things? Some theorists have proposed that tachyons could be tied to dark energy, or that they might form a background field affecting the expansion of the universe. Others believe tachyons could help explain entanglement, how two particles can appear connected instantly over vast distances. Maybe the link isn't spooky, maybe it's superluminal. These ideas are speculative. None have been confirmed, but they serve a purpose. Tachyons stretch our imagination. They poke at the limits of relativity. They remind us that just because something feels impossible doesn't mean it's meaningless. They also raise deep questions about the nature of information, time, and reality. If faster-than-light particles exist, would they be visible, detectable? Could we ever interact with them? Or would they remain forever out of phase with our world, existing in a domain we can't touch? It's possible that tachyons are simply ghosts in the equations, dead ends, symbols of instability, and nothing more. But it's also possible that they're clues, echoes of a deeper theory, a universe where time isn't fixed, where causality is flexible, where the speed of light is not a ceiling, but a boundary between two domains, one we know, and one we've only imagined. Spontaneous symmetry breaking. At the heart of the universe lies symmetry, not just visual symmetry, like mirrored shapes or balanced patterns, but deep mathematical symmetry, the kind that governs forces, particles, and the laws of physics themselves. But curiously, the universe we see is not perfectly symmetric. Some forces are stronger than others. Some particles have mass, while others don't. The world has structure, direction, difference. So what happened? The answer is one of the most powerful ideas in modern physics: spontaneous symmetry breaking. Let's begin with something simple. Imagine a perfectly round table with a ball placed exactly in the center. The system is completely symmetric. There's no preferred direction. But now imagine the ball rolls slightly toward one side. The symmetry is broken, not by the table, but by the choice the ball made. The laws remain symmetric, but the state of the system isn't. That's spontaneous symmetry breaking, when the underlying rules are symmetric, but the outcome chooses a direction anyway. And this idea, it's everywhere in physics. Take a magnet. Above a certain temperature, the atoms inside are pointing randomly. No net magnetism. The system is symmetric in all directions, but as it cools, the atoms suddenly align, pointing in the same direction. The symmetry is spontaneously broken, and a magnetic field appears. The rules didn't change, but the system did. In particle physics, spontaneous symmetry breaking plays an even deeper role. It explains why particles have mass. According to the Standard Model, before a certain point in the early universe, all particles were massless. The laws were fully symmetric: photons, electrons, W and Z bosons. They were all on equal footing. Then came the Higgs field, a scalar field that filled all of space like an invisible mist. As the universe cooled, the Higgs field settled into a stable configuration, but not at zero. It chose a non-zero value, a direction in field space. And just like the ball on the round table, this choice broke the symmetry. Particles that interact with the Higgs field gained mass. Others, like the photon, didn't. The electroweak symmetry was broken, and suddenly the forces separated. Electromagnetism and the weak nuclear force became distinct. It's one of the most elegant mechanisms in physics. A field chooses a ground state. The symmetry is hidden, and the properties of particles change as a result. But it's not just about mass. Spontaneous symmetry breaking is also at the heart of phase transitions like water freezing or metals becoming superconductors. It's the driving force behind the structure of atomic nuclei, the behavior of condensed matter, and even the patterns of galaxies. And it's deeply tied to Goldstone's theorem, which says that whenever a continuous symmetry is spontaneously broken, a massless particle, called a Goldstone boson, emerges. In condensed matter physics, these are phonons. In particle physics, some versions of symmetry breaking predict new particles we haven't discovered yet. But what's truly fascinating is how hidden symmetry can still guide reality. Even when symmetry is broken, it leaves behind patterns, residual effects, clues that it was once there. The broken symmetry becomes a template for complexity. It's like cracking an egg. Once it's broken, the shell can't be put back together, but its shape still tells you it used to be whole. This is also where cosmology enters the picture. In the early universe, as the cosmos expanded and cooled, it likely passed through multiple symmetry-breaking events, each one changing the landscape of physics, each one setting the stage for the next layer of structure to emerge. Some theories suggest that cosmic inflation, dark energy, and even the matter-antimatter imbalance may be linked to spontaneous symmetry breaking on grand scales. And in theories beyond the standard model, like supersymmetry or grand unification, the process of breaking symmetries becomes even more important. Because symmetry gives you beauty, but breaking symmetry gives you structure. And without structure, you can't have stars, atoms, molecules, life. The symmetry must break for the universe to build. So what does this mean on a deeper level? It means the universe doesn't just follow rules. It emerges from choices. From states that fall into valleys of potential energy, selecting one outcome among many. It means that the apparent asymmetry of the world, the difference we see between forces and particles, isn't a flaw. It's a result of deeper hidden order. It's a creative tension, a dance between balance and imbalance. And perhaps in some fundamental sense, the universe is not symmetric despite the laws. It's asymmetric because of them. That moment when symmetry breaks, it's not destruction. It's birth, the many worlds interpretation. Close your eyes for a moment and imagine this. You flip a coin, heads or tails. In our everyday world, it feels like only one outcome becomes real. Maybe it lands on heads and that's that. But what if both outcomes actually happened? What if the universe split, with one version of you watching the coin land heads and another version watching it land tails? That's the strange, stunning idea behind the many worlds interpretation of quantum mechanics. Let's rewind for context. In quantum mechanics, particles aren't little dots, they're wave functions, probabilities, clouds of possible outcomes, until you measure them. When you observe a particle, its wave function collapses, and you see just one result. One location, one energy, one spin. It's like the universe chooses an outcome and discards all the others, or so we thought. The traditional view, the Copenhagen interpretation, says observation causes the collapse, that the wave function is just a tool for calculating outcomes, not a real thing. But in 1957, physicist Hugh Everett had a different idea. What if the wave function never collapses? What if it keeps evolving smoothly, deterministically? And what if, instead of one outcome becoming real, all outcomes become real, but in separate, branching universes? This is the many worlds interpretation. When you flip a coin, the universe splits. In one branch, it's heads. In another, it's tails. When you observe an electron, every possible measurement outcome happens in parallel universes that now evolve independently. It's not just metaphysical musing. It's a serious interpretation of the Schrödinger equation. No collapse, no special role for observers, just pure unbroken quantum evolution, and it solves some big problems. For example, what causes wave function collapse? In many worlds, that question vanishes. There is no collapse, just branching. It also restores determinism. The quantum world under many worlds is entirely deterministic. It only looks random to us because we're inside one branch, unaware of the others. Each time a quantum event occurs, the universal wave function splits, and we become entangled with one of the results. In that sense, your consciousness also branches, copying itself into new versions, each experiencing a different path through the quantum multiverse. It sounds bizarre, but it's mathematically clean. It's also hard to test, because once the universe branches, each branch becomes inaccessible to the others. There's no signal we can send to confirm the other branches exist, no way to reach across the divide. And yet, some physicists take it seriously. Why? Because it removes the need for arbitrary rules, no need for measurement-induced collapse, no need for a special observer, just one elegant, consistent wave function describing the entire universe. And that universe isn't shrinking, it's expanding into a vast branching tree of possibilities. Every decision, every particle, every outcome, it all happens somewhere. And if that's true, it changes how we think about everything. There is a version of you that chose a different job, a version that missed a bus and met someone new, a version that didn't hit send on that one message. An endless sea of versions, some similar, some radically different. In fact, the many worlds interpretation suggests that what we call the universe is just one branch among countless others. What we call reality is just a thin slice of something much larger. It raises philosophical questions too. If every possibility happens, what does it mean to choose? If your mind splits with every outcome, what defines you? And does this infinite branching devalue your actions or make them more meaningful? Different physicists feel differently. Some embrace the elegance of the theory, others reject it as too extravagant. Occam's razor, they say, don't multiply universes without necessity. But even critics agree, the math works. The many worlds interpretation is a valid solution to the equations of quantum mechanics, and it forces us to reconsider what reality actually means. Because maybe the universe isn't a single thread. Maybe it's a tapestry, a constantly branching, infinitely detailed web of possibilities, each one just as real as the one you're experiencing right now. And somewhere in one of those branches, another version of you is hearing this same sentence, wondering the exact same thing. The cosmological constant problem. There's a number written into the equations of the universe. A tiny number. Quiet. Mysterious. Easy to overlook. But it shapes everything. It determines how fast the universe expands, how galaxies move apart, whether the cosmos will keep growing forever or collapse back in on itself. That number is called the cosmological constant, usually represented by the Greek letter lambda. Lambda. And the problem? Our best theories predict it should be enormous, so large that the universe should have blown apart the moment it began. But in reality, it's not. In fact, it's tiny, about 120 times smaller than expected. This is the cosmological constant problem, and it's one of the biggest unsolved mysteries in modern physics. Let's take it from the top. In 1917, Einstein added the cosmological constant to his equations of general relativity. At the time, he thought the universe was static, not expanding or contracting. But gravity pulls things together, so to balance that, he introduced lambda as a repulsive force, a kind of built-in anti-gravity that counteracted gravity's pull. Later, when it was discovered that the universe is expanding, Einstein dropped the term and called it his biggest blunder. But in the 1990s, something strange happened. Astronomers observing distant supernovae found that the expansion of the universe isn't slowing down. It's speeding up. There had to be something pushing galaxies apart, something repelling space itself. So the cosmological constant came back, with a vengeance. Today, we think of lambda as representing the energy density of empty space, what's sometimes called dark energy. But here's where things get weird. According to quantum field theory, even empty space isn't really empty. It's filled with vacuum fluctuations, tiny particles constantly popping in and out of existence. These fluctuations carry energy. And if you add up all that energy, the energy of the vacuum itself, you get a number, a value for the energy density of space. But when physicists calculate that value, it's enormous, catastrophically large. So large, in fact, that if it were correct, the universe would have expanded so violently that atoms couldn't form. Galaxies wouldn't exist, stars wouldn't shine, life would be impossible. But when we measure the actual cosmological constant through astronomical observations, we find a value that is 120 orders of magnitude smaller. That's a 1 followed by 120 zeros. It's the biggest mismatch between theory and observation in the history of physics. So what's going on? There are a few possibilities. One is that there's some kind of hidden symmetry, some deep mechanism in the laws of physics that cancels out the vacuum energy almost perfectly. We haven't discovered it yet, but it might explain why lambda is so small. Another idea comes from string theory and the multiverse. If there are countless universes, each with different values of the cosmological constant, then maybe we just happen to live in one of the rare universes where lambda is small enough for galaxies to form. That's the anthropic argument. We observe a life-permitting value because otherwise we wouldn't be here to observe it. It's not satisfying to everyone, but it's logically consistent. Then there's the idea that maybe lambda isn't constant at all. Maybe what we call dark energy evolves over time. Maybe it's dynamic. Maybe we've only observed a brief snapshot of something deeper, something that changes as the universe grows. That's the idea behind quintessence, a kind of evolving energy field that mimics a cosmological constant, but with a twist. Still, none of these ideas have been confirmed. We're left with a mystery. The vacuum should be filled with energy. That energy should curve space-time. It should make the universe expand at a mind-bending rate. But it doesn't. Why? We don't know, and that's why the cosmological constant problem is so haunting. It suggests that our understanding of quantum fields, or gravity, or both, is incomplete. It tells us there's something missing, some hidden layer of reality we haven't yet uncovered. And it reminds us that even something as empty as space isn't truly empty. It's full of potential, full of tension, full of unanswered questions. The vacuum isn't quiet. It's a puzzle. One whose solution might lead us to a new theory of physics, a new understanding of space, time, and the true nature of the universe. Until then, lambda remains a whisper, a riddle, a number that shouldn't exist, but somehow does. Feynman path integrals. Imagine tossing a ball. In our everyday experience, it follows a single clear arc. One path, predictable and smooth. Now zoom down, way down, to the quantum level. Toss an electron instead. Suddenly, all bets are off. Because in quantum mechanics, the electron doesn't just follow one path. It explores every possible path simultaneously. Not just the straight line, but the zigzag, the loop, the impossible detour through space and time. This bizarre yet beautiful idea comes from the mind of Richard Feynman, a physicist known for his genius, his storytelling, and for giving us one of the most elegant frameworks in quantum theory, the path integral formulation. Let's take it slow. In standard quantum mechanics, we describe particles with wave functions. We evolve those wave functions using Schrödinger's equation, and we calculate probabilities for outcomes. But Feynman had a different way of looking at things. Instead of focusing on the wave function's evolution, he asked, what if we calculate the probability of a particle going from point A to point B by adding up contributions from every possible path it could take between those points? That's the heart of the Feynman path integral. Each path contributes a complex number or amplitude based on the action along that path. Some contributions interfere constructively, others cancel out. But when you sum over all paths, and we really do mean all, you get the total amplitude for the transition. It's like imagining a particle simultaneously walking every route through a city, down every alley, every side street, every rooftop, and somehow the interference of all those paths tells you where the particle is most likely to be. And the magic? This approach gives the same answers as Schrödinger's method, but it also gives us a powerful new way to think about physics, especially in quantum field theory and beyond. Let's dig a little deeper. In classical physics, a system follows the path of least action, a principle going all the way back to Lagrange and Hamilton. That's the path that minimizes, or more accurately, extremizes, the quantity called action, which is basically a measure of how a system evolves. In Feynman's version, all paths matter, but paths close to the classical one tend to contribute more constructively because their phases are more aligned. Wild, erratic paths contribute less because their phases cancel each other out. So even though quantum particles explore every possibility, the classical path still emerges as the dominant behavior at large scales. It's a beautiful bridge between quantum mechanics and classical physics. But Feynman path integrals go far beyond particles. They're used in quantum electrodynamics, quantum chromodynamics, and even in speculative theories like quantum gravity and string theory. In these theories, we don't just sum over particle paths, we sum over fields, geometries, even entire space-time configurations. Path integrals give us a way to describe how forces work at a distance, how particles interact, how virtual particles flicker in and out of the vacuum. They're at the core of how we calculate Feynman diagrams, those elegant squiggly line illustrations that describe particle interactions in quantum field theory. Each line, each loop, each vertex corresponds to a term in the path integral. Without Feynman's approach, modern particle physics wouldn't exist. It's also one of the few formulations that works naturally in relativistic settings, making it ideal for connecting quantum mechanics with special relativity. And there's another surprising application: statistical mechanics. In certain cases, the math of quantum path integrals maps directly onto the math of thermodynamics. That means techniques used in quantum physics can help describe systems like magnets, fluids, or materials at phase transitions. The idea of summing over possibilities shows up in probability theory, finance, machine learning, and more. Feynman's insight echoes far beyond physics, but at its core, the path integral formulation is a philosophy. It tells us the world isn't deterministic in the classical sense. Particles don't follow a single route. Instead, nature explores all options. The ones that interfere constructively build the reality we observe. The others fade out in a blur of probabilities. So what does this mean for us? It means that even in a universe governed by uncertainty, patterns emerge. It means that complexity can arise from simplicity. And it means that what we call the path taken is just one visible thread in a tapestry woven from infinite invisible threads, paths never seen, but always considered. Feynman once said, "I think I can safely say that nobody understands quantum mechanics." And yet, his path integrals give us a way to navigate its strangeness with clarity. They remind us that nature doesn't follow a single plan, it tries them all. And somehow, out of that chaos, comes the world we see, emergent space-time. We often think of space and time as the backdrop of everything, a silent stage where matter and energy play out their roles. You are somewhere, and it's now. Those seem like the most basic facts of existence. But what if space and time aren't fundamental? What if they're not the stage, but part of the story? What if space-time itself is a product emerging from something deeper, more abstract? Welcome to one of the boldest ideas in theoretical physics, emergent space-time. Let's begin with the basics. In general relativity, space-time is a smooth fabric. Mass and energy bend it, and that bending creates gravity. It's continuous, geometric, fundamental. But in quantum mechanics, the world is granular, discrete, probabilistic, described not by points and curves but by wave functions and entanglement. And when you try to combine the two, gravity and quantum mechanics, something strange happens. The math suggests that space and time might not be built-in ingredients, but consequences of something more fundamental. That idea, that geometry emerges from deeper quantum rules, has been gaining traction, and one of the key clues, quantum entanglement. In recent years, physicists exploring the boundary between quantum mechanics and gravity have noticed something extraordinary. The amount of entanglement between different parts of a quantum system seems to create geometry. In other words, the pattern of quantum connections gives rise to distance. Two particles that are highly entangled are closer, even if they're physically far apart. Entanglement weaves the threads of space-time itself. This leads to the idea that space is not a container, but a network built from information, a kind of quantum web, and the more connections in that web, the more space emerges. One of the boldest expressions of this idea comes from ADS-CFT correspondence. In this duality developed in string theory, a universe with gravity, like the inside of a 3D space, is exactly equivalent to a quantum system on its 2D boundary, with no gravity. It's like a cosmic hologram. Everything that happens inside the universe is encoded on a surface with no depth. And in this holographic setup, geometry is built from quantum entanglement. It's not just poetic, it's mathematical. This has led to wild new theories, like the idea that black holes might be quantum computers, or that the interior of a wormhole might be stitched together from entangled pairs. Even the famous quote, ER equals sign EPR, suggesting that Einstein-Rosen bridges, wormholes, and entangled particles, EPR pairs, are different faces of the same phenomenon, points to this emergent idea. Space-time is not just bending under gravity, it's forming from information itself. But how does that work? Physicists are still exploring. Some models use tensor networks, where space is represented as a network of mathematical nodes and connections. Others use loop quantum gravity, where space is made of tiny loops of geometry. Still others explore spin networks, causal sets, or entropic gravity. Different paths, same idea. Space-time is not a given, it's a result. And if that's true, then time might not be fundamental either. Instead, it might arise from quantum correlations, entropic flow, or observer relationships. What we call now might just be a slice of a deeper, timeless reality. This would also explain why gravity has been so hard to quantize. Maybe we've been treating it like a force, when it's actually an emergent phenomenon, like temperature. You don't quantize temperature directly, you quantize molecules, and temperature arises statistically. Maybe space and gravity are like that too. This idea also ties in with black holes. Black holes are mysterious. Their entropy is proportional to their surface area, not volume. Their information storage capacity is massive, and their thermodynamic properties suggest that they might be windows into the quantum structure of space-time. Maybe black holes are where the threads of space break down. Maybe that's where the illusion of geometry unravels. So what does this mean? It means we might be living in a universe where space isn't out there. It's woven in here, built from the most abstract ingredients: logic, probability, and quantum entanglement. It means that time isn't ticking like a clock, but emerging like music from the structure of the system. And it means the very fabric of reality might not be fabric at all. It might be code, connections, context. A universe not of points in space, but of relationships that give rise to the illusion of space. In that view, distance is relative not just in the Einsteinian sense, but in the quantum sense. Things are near because they're entangled, far because they're not. And you're not in space. You're part of the network. Entropy and the arrow of time. Let's start with something simple. Crack an egg. Now try uncracking it. Impossible, right? The egg splatters, the yolk mixes, the shell breaks. But once it's broken, it stays broken. That's not just a matter of practicality. It's a deep law of physics. And it comes down to a quiet, powerful idea: entropy. Entropy is one of those words that gets thrown around a lot, especially when things are messy. That room's a mess. Entropy wins again. But at its core, entropy isn't just about disorder. It's about possibilities. It's about the way systems evolve. And it's at the very heart of a mystery that's been puzzling scientists and philosophers for centuries. Why does time only move forward? Because when you look at the fundamental laws of physics, the ones that govern motion, gravity, even quantum mechanics, they're symmetric. They don't care if time moves forward or backward. Mathematically, most of them work just fine in either direction. So why can't we reverse a broken egg? Why do we remember the past but not the future? Why do we grow older but never younger? The answer lies in the second law of thermodynamics. In an isolated system, entropy tends to increase. Let's break that down. Entropy, in its simplest form, is a measure of how many different ways a system can be arranged. Think of it as the number of microscopic configurations that look the same from a big-picture perspective. A neat stack of cards, low entropy. A shuffled deck, high entropy. There are far more ways for the cards to be randomly arranged than perfectly ordered. So when you crack that egg, you're moving from a highly ordered, low entropy state, egg intact, to a high entropy one, egg splattered. And statistically, there are way more splattered egg configurations than unbroken ones. That's why it's so easy to go in one direction and so impossible to go the other way. The arrow of time, the fact that time has a direction, is deeply connected to this flow of entropy. But here's the curious part. The equations that describe atoms, electrons, even stars, don't include any arrow of time. They don't point forward. They just are. The only law that does care about direction, the one that gives us the sensation of before and after, is entropy. This subtle statistical law shapes our entire experience of reality. Now zoom out to the universe itself. At the beginning of time, right after the Big Bang, the universe was incredibly hot, dense, and strangely low in entropy. That's weird because you'd think something so energetic and chaotic would be high entropy, but it wasn't. The energy was spread out very evenly. And that evenness, that balance, meant there was a lot of room for entropy to grow. So from that moment onward, the universe has been sliding down the entropy slope. Stars form, stars die, galaxies cluster, systems evolve, and entropy keeps increasing. Every process, every breath, every decaying leaf, every burning star is part of that cosmic expansion of possibility, of randomness, of disorder, of change. And that gives time its direction. In a world without entropy, time wouldn't have a flow, it would just be a dimension, like width or height. But because entropy increases, we feel time. We experience its arrow, always pointing forward, never back. Now let's look at entropy in more familiar places. Open your phone, type a message, delete a file, play a video. All of those actions increase entropy in some way, usually in the form of heat, energy use, or information loss. Every computer, every machine, every living cell operates by increasing entropy. It's not a bad thing, it's just what the universe does. And that has some fascinating consequences. For one, heat death. If the universe keeps expanding, keeps increasing entropy, eventually everything will settle into a uniform, low-energy state. No stars, no structure, just evenly spread particles. Maximum entropy, no more change. No more before or after, just stillness. That's called the heat death of the universe, the theoretical endpoint of entropy's journey. But don't worry, it's trillions of years away. Still, it makes you wonder. If the universe started in a low entropy state, why? How? That's a mystery we haven't solved. Some physicists think it's a question of initial conditions, an accident of the Big Bang. Others believe entropy is tied to gravity in subtle ways we don't fully understand yet. Here's something even more puzzling. In quantum mechanics, the act of measuring a system creates a kind of direction in time. When you observe a particle, its wave function collapses. It chooses a state. That process seems to break time symmetry, but many interpretations suggest that's just our perception of measurement, that maybe time doesn't collapse anything at all. And then there's the link between entropy and information. In the 20th century, physicist Claude Shannon connected entropy to information theory. Basically, the more unpredictable a message is, the higher its entropy. A random string of characters? High entropy? A repeating pattern? Low entropy. So in a strange way, entropy isn't just about heat and molecules. It's about knowledge, uncertainty, possibility. Even black holes, those cosmic vacuum cleaners, obey the rules of entropy. When something falls into a black hole, its entropy increases, and physicists discovered that the surface area of the black hole is related to its entropy. This led to the famous idea that information might not be destroyed in a black hole. It might be stored on its surface. Which brings us back to that idea again, that the universe has rules. Strange, counterintuitive rules, but consistent ones. Entropy doesn't just make eggs break and coffee cool, it makes time move. It gives our lives a direction, a story, a flow. Without entropy, there'd be no memory, no evolution, no growth, nothing to separate yesterday from tomorrow, just a static, frozen universe. But because entropy increases, we have history, we have change, we have time. And even though we can't reverse it, we can understand it. Entropy may feel like decay, like disorder, but it's also freedom. It's variety. It's the space for things to happen. And in a strange way, it's the engine of complexity, of life, of motion. So next time something breaks, falls apart, or dissolves into randomness, remember, it's just entropy doing its job, guiding time forward, expanding possibilities, telling the universe's story, one irreversible moment at a time. Bell's theorem. There is a moment in every deep dive into quantum physics where something snaps. It's that realization that the universe might not just be weird, but that it might be fundamentally different from how we think about space, time, and even reality itself. That moment often comes with Bell's theorem. To really understand what makes this idea so powerful and so unsettling, we need to start with a question. Is the world fundamentally connected in a spooky, invisible way? Or is everything still local and independent, even at the quantum level? That's where Bell's theorem steps in. But let's rewind. Let's start with entanglement, a phenomenon where two quantum particles become linked in such a way that their properties are instantly correlated, no matter how far apart they are. Let's say you create two entangled photons. They shoot off in opposite directions, maybe across a room, maybe across the galaxy. Now, you measure the polarization of one photon, and instantly the other one knows how to respond. The results are correlated every time. Einstein hated this. He called it spooky action at a distance, and insisted there had to be some hidden variables, something local and physical, carrying instructions that made the photons behave the way they did. In other words, he believed the universe was local and realistic. Local, meaning nothing can affect something else faster than the speed of light. And realistic, meaning particles have definite properties, even if you don't measure them yet. But here's where things get wild. In 1964, physicist John Bell proposed a test, a mathematical inequality. It said if Einstein's view is correct, if hidden variables exist and the universe is local, then certain statistical patterns should show up when you measure entangled particles. This was Bell's genius. He didn't just argue. He gave us an experiment. It's called Bell's inequality. And when physicists started testing it in the 1970s, and more rigorously in the decades that followed, they found something shocking. Nature violated Bell's inequality. The experimental results didn't line up with a local hidden variable theory. Over and over, the measurements showed stronger correlations than any classical local theory could explain. That means either information is traveling faster than light somehow, or particles don't have definite properties until they're measured. In both cases, something deep is broken in our classical worldview. Let's sit with that for a second. Imagine two people on opposite ends of the earth flipping coins, and somehow, every time one person flips heads, the other one flips tails. Every time. No communication, no delay. Just perfect correlation instantly. That's not random, that's something deeper. And this isn't just theoretical. Experiments have refined this process again and again, closing loopholes, improving detectors, and spacing the measurements far enough apart that no signal could possibly be traveling between them fast enough to coordinate the outcome. Still, quantum mechanics wins, every time. So what does Bell's theorem really say? It says the universe is either not local, meaning that entangled particles are somehow connected in a way that transcends space, or not realistic, meaning particles don't have predetermined properties. They only choose their state when measured. Either way, our intuitions about reality, the idea of independent objects existing with their own definite properties, don't hold up. It's worth noting that Bell didn't show that quantum mechanics is spooky. He showed that if you believe in locality and realism, then quantum mechanics can't be right. And since quantum mechanics has been proven accurate over and over again, the implication is unavoidable. Reality is either non-local or non-real. This has sparked all sorts of philosophical debates and interpretations. Some physicists say, okay, fine, reality is non-local. There's a web of instantaneous influence connecting things. Others say, no, it's not about faster-than-light signals. It's about the fact that particles don't have fixed properties until we look. Then there's the many worlds interpretation, which dodges the problem altogether by saying every possible measurement outcome happens, just in separate branches of the universe. There's no randomness, no faster-than-light influence, just branching realities. But whatever interpretation you prefer, Bell's theorem is the dividing line. It forces the issue, and before Bell, you could sort of believe that quantum weirdness was just a mathematical trick. After Bell, you can't hide from it. Quantum entanglement is real. Bell's inequality is violated. The universe is more connected or more fundamentally undefined than we ever expected. And what's truly beautiful is how Bell's theorem transformed a philosophical debate into a physical test. It turned an argument about what reality is into something you could verify in a lab, with particles and detectors and data. That's powerful. That's physics at its best. It's not just that the universe is strange, it's that the strangeness is testable. And now, those same principles are being used in quantum computing and quantum cryptography, technologies that exploit entanglement and non-locality to do things we never thought possible. Quantum teleportation? Real. Quantum encryption? Real. It all flows from the implications of Bell's work. So, next time you think of the universe as made of solid, separate things, objects with clear properties, remember Bell's theorem. It quietly whispers that everything might be connected, or nothing might be real until you look. Either way, the universe is wilder than we imagined. Non-locality in quantum mechanics. Imagine holding two gloves, one in your left hand, one in your right. You put each glove into a sealed box, then ship one box to the other side of the galaxy. Later, someone opens the box near the Andromeda galaxy and finds the right glove. Instantly, you know the one near you must be the left glove. No surprise. That's just common sense. But in the quantum world, things don't work like that. Because in quantum mechanics, when two particles are entangled, it's not just that knowing one tells you something about the other. It's that measuring one appears to affect the state of the other instantly, no matter how far apart they are. This strange connection is called non-locality, and it's one of the most unsettling features of quantum mechanics. To understand why this is such a big deal, let's start with entanglement. Entanglement happens when two quantum systems interact in such a way that their states become linked. From then on, the state of one can't be fully described without also describing the other, even when they're separated, even when they're light years apart. It's as if they become part of a single invisible system, no longer two, but one. Now, in classical physics, if two objects are far away from each other, they can't influence each other instantly. That's the idea of locality, that causes and effects are limited by the speed of light. But quantum mechanics breaks that idea. Because when you measure one entangled particle, the outcome of the measurement on the other particle becomes instantly defined. Einstein hated this. He called it spooky action at a distance and insisted there had to be some deeper mechanism, some hidden variables that made the results look correlated. He thought quantum mechanics was incomplete. But then came Bell's theorem and the experiments that followed, and they showed that no theory based on local hidden variables could explain the correlations we see in entangled particles. This wasn't just a weird philosophical debate, it was measurable, testable, reproducible. Nature, it seems, really is non-local. That doesn't mean faster than light communication. It doesn't mean you can send a signal instantly from here to another galaxy. Quantum non-locality doesn't violate special relativity because the results of any individual measurement are still random. You can't control them. But it does mean that the outcome of one measurement is tied to the outcome of the other, even across vast distances, with a precision that defies any classical explanation. It's as if reality doesn't care about space, as if space is just a convenience, a framework, and underneath, everything is part of a single holistic system. Non-locality tells us that the universe isn't built from independent parts, each evolving separately. It's built from relationships, from correlations, from patterns that stretch across space without being limited by it. This has enormous implications. In fact, some physicists now believe that space itself might emerge from entanglement, that the geometry of space, its curves, distances, even its dimensionality, arises from the structure of quantum correlations. In this view, entanglement is more fundamental than space. Think about that. Space isn't the backdrop. It's the product of deeper, more abstract quantum connections. Where things are and how far apart they appear might be illusions, emergent properties of a deeper entangled network. Some interpretations of quantum mechanics, like the pilot wave theory, try to preserve locality, but only by introducing other non-classical features. Others, like the many worlds interpretation, avoid non-local influences by splitting the universe into branches. But no matter how you interpret it, the data is clear. Quantum mechanics doesn't obey classical locality. It's non-local by nature. And this non-locality isn't just a curiosity, it's being put to work. In quantum computing, entangled qubits allow for parallel processing that outpaces anything classical computers can do. In quantum cryptography, entanglement can be used to detect eavesdropping and ensure secure communication. There are even proposals for quantum teleportation, not of matter but of quantum information, based entirely on entanglement and non-locality. It's real, it's useful, and it forces us to rethink what distance really means. So where does that leave us? In a universe where the most fundamental connections aren't bound by space, where two particles can influence each other without anything crossing the space in between, where the very fabric of reality might be stitched together not by matter or energy, but by invisible instant correlations that reach beyond what we can see. Non-locality reminds us that our intuitions, built on everyday experience, don't always match the deep structure of the universe. We think in terms of here and there, before and after, cause and effect traveling through space. But nature doesn't always follow that script. In the quantum realm, distance doesn't define connection. Space doesn't always limit interaction, and sometimes the universe acts as if it's a single, undivided whole. It's strange. It's beautiful. And it might just be the key to understanding what reality really is. The Pauli exclusion principle. Let's zoom in. Down past the skin, past the cells, past the atoms. until we're looking at the tiniest building blocks of everything. Electrons, they're tiny, they're invisible, and yet, thanks to one elegant rule, they're the reason you're not sinking through your chair right now. This rule is called the Pauli exclusion principle, and it explains why atoms don't collapse, why matter holds its shape, why the periodic table has structure, and why the universe doesn't fold in on itself like a paper lantern. So, what is it? The Pauli exclusion principle is a law of quantum mechanics that says no two identical fermions can occupy the same quantum state at the same time. Let's unpack that. Fermions are particles like electrons, protons, and neutrons, particles that make up matter. They're different from bosons, which are force-carrying particles like photons and gluons. Fermions have half-integer spin, a quantum property that's kind of like intrinsic angular momentum. Now here's where it gets weird. In the quantum world, particles don't sit still with little name tags on them. You can't point and say, "That's Bob the electron, and he's at position A." Instead, each particle is described by a wave function, a spread-out probabilistic cloud of where it might be and how it might behave. What Pauli discovered is that two electrons can't occupy the exact same state. Not just the same location, but the same energy level, spin orientation, orbital configuration, everything. If you try to force them into the same state, quantum mechanics pushes back. The wave functions twist apart. The electrons repel, not just because of electric charge, but because of identity. And that tiny rule? It holds the entire structure of matter in place. Take atoms. In the nucleus, protons and neutrons are packed together, and around them, electrons whirl in orbitals. Because of the exclusion principle, you can't have all the electrons sitting in the lowest energy orbital. Only two can go there, one with spin up, one with spin down. After that, the next electrons have to climb to higher orbitals. That's why atoms have layers, why the periodic table has rows, why elements behave differently depending on how many electrons they have. Without the Pauli exclusion principle, all electrons would pile into the same lowest state. Atoms wouldn't have structure, chemistry wouldn't exist, matter would collapse into a soup of sameness. In short, you wouldn't be here. But it gets even more profound. In massive stars, especially white dwarfs and neutron stars, gravity tries to crush matter down into the tiniest possible space. But even as gravity pulls inward, the exclusion principle fights back. In white dwarfs, it's electrons that resist compression. In neutron stars, it's neutrons. This resistance creates a type of pressure, degeneracy pressure, that holds the star up against gravity. It's not thermal pressure, it's not motion, it's quantum identity. In fact, a white dwarf stops collapsing not because it's hot, but because electrons refuse to be in the same state. That refusal holds up something as massive as a star. Think about that. A fundamental law of quantum behavior written into the wave function of tiny particles is strong enough to fight the collapse of entire suns. It's a quiet force, but it's everywhere. The Pauli exclusion principle also shapes the behavior of solid materials. It's why metals conduct electricity the way they do, why semiconductors work, why certain materials behave magnetically. The energy bands in solid-state physics, the basis of modern electronics, all rely on this principle. And it all traces back to one idea: no two identical fermions in the same state. So where did it come from? The principle was formulated in 1925 by Wolfgang Pauli before quantum mechanics was fully developed. He proposed it to explain patterns in atomic spectra, lines of light emitted by excited atoms. Later, with the development of quantum field theory, The exclusion principle found deep mathematical roots. It arises from the anti-symmetric nature of fermionic wave functions. When you swap two identical fermions, the wave function flips sign. If they were in the same state, the wave function would cancel itself out, leaving nothing. Nature simply doesn't allow it. This symmetry, or rather anti-symmetry, is baked into the mathematics of reality. It doesn't just describe how particles behave, it defines what kind of particles can exist. Fermions obey the Pauli exclusion principle. Bosons don't. That's why photons can pile into the same laser beam, but electrons can't crowd into the same orbital. It's one of the most important divisions in the entire standard model of particle physics. And here's something beautiful. This principle, which begins in the abstract math of wave functions, ripples out across the cosmos. It explains why atoms form structures, why stars can shine without collapsing, why there's variety in the elements, why the universe has complexity instead of uniformity. All because certain particles can't be in the same place doing the same thing. It's a law of limits, a built-in individuality, a cosmic rule that says every electron deserves its own space, and because of that we get molecules, crystals, DNA, life. We get structure instead of collapse, diversity instead of monotony, resistance instead of surrender. The Pauli exclusion principle doesn't just prevent chaos, it creates everything stable, everything interesting, everything you. The Planck scale. There's a limit to how far you can zoom in, a boundary not of matter but of meaning, a place where our best theories, relativity and quantum mechanics, start to crumble, not because they're wrong, but because they can't both be right at the same time. That boundary is called the Planck scale. It's the scale where space, time, energy, and information all start to blur. Named after physicist Max Planck, who helped launch quantum theory in the early 20th century, the Planck scale represents the smallest meaningful unit of length, time, and energy. Let's start with the basics. The Planck length is about 1.6 × 10^35 meters. That's 20 orders of magnitude smaller than a proton. The Planck time is about 5.4 × 10^44 seconds, the shortest interval of time that could theoretically make sense. The Planck energy is around 1.22 × 10^19 GeV, an energy so high it's far beyond anything we can reach in any particle collider. These units aren't just tiny, they're fundamentally significant. They represent the limits of our current understanding of physics. Why? Because that's where the effects of quantum mechanics and general relativity become equally strong and incompatible. Let's explore that. General relativity describes gravity as the curvature of space-time. It works beautifully at large scales, planets, stars, galaxies. Quantum mechanics describes the behavior of particles and forces at small scales. It works brilliantly with atoms, electrons, photons. But the Planck scale is where these two worlds collide. Try to probe a region smaller than the Planck length, and you need so much energy that you'd create a black hole just by trying to look. That's right, your measurement would collapse the region into a gravitational singularity. It's not just that we can't measure anything smaller, it's that space-time itself may not exist in any familiar way at those scales. This leads physicists to believe that space and time are not continuous. At the Planck scale, they might be quantized, made of indivisible chunks like pixels on a screen, but for reality itself. In fact, several quantum gravity theories predict this. Loop quantum gravity describes space as woven from loops of discrete geometry. String theory replaces point particles with tiny, vibrating strings, whose size is on the order of the Planck length. Causal set theory suggests that space-time is made from a series of discrete events, like dots on a graph, linked by cause and effect. In each case, the smooth fabric of space-time breaks down into something granular. The Planck scale is the quantum of geometry. It's also where quantum foam might bubble, an idea proposed by John Wheeler. At those tiny scales, space-time could be wildly fluctuating, with tiny wormholes and folds popping in and out of existence, like the surface of a boiling pot. But because the Planck scale is so extreme, we've never observed it directly. We don't have microscopes powerful enough. We don't have energy levels high enough. Even the Large Hadron Collider, the most powerful particle accelerator ever built, operates at energies 1 trillion times too low to probe the Planck scale. So how do we study it? Mostly through theory, through mathematical models, through the edges of black hole physics and the early moments of the Big Bang, where Planck scale effects might leave behind indirect clues. Some speculative ideas even suggest that quantum fluctuations at the Planck scale could influence the structure of the universe at the largest scales, seeding galaxies, shaping cosmic expansion, or creating ripples in space-time we might one day detect. And yet, despite all our theories, the Planck scale remains a mystery, a veil, a border between what we know and what we imagine. It's a humbling reminder that even the most advanced science has limits, that no matter how deep we look, there's always something beyond. And maybe that's what makes the Planck scale so profound. It marks the place where our understanding ends, not because we're not clever enough, but because reality itself might be different there. Beyond that boundary, space may dissolve, time may fade, matter, energy, and information may merge into something we don't yet have the language to describe. But that's exactly where the next great revolution in physics is waiting. At the edge of the knowable, at the Planck scale, time reversibility and fundamental laws. There's something comforting about the way time moves, from past to future, from cause to effect, from memory to possibility. We experience it like a flowing river, always forward, never back. But here's the strange part. Most fundamental laws of physics don't care which way time flows. Flip the arrow, run the equations backward, and everything still works. This is called time reversibility or time symmetry, and it's one of the quietest yet most profound mysteries in all of physics. Let's start with classical mechanics. Newton's laws, for instance, are fully time reversible. If you film a collision between two billiard balls, then play it backward, the motion still obeys the same laws. Momentum is conserved. Energy is conserved. Nothing breaks. Same with electromagnetism. Maxwell's equations, describing electric and magnetic fields, don't mind if time runs forward or backward. Even quantum mechanics is time symmetric, at least in its core equations. The Schrödinger equation, which governs the evolution of quantum systems, works just as well in reverse. So then, where does the arrow of time come from? Why do we remember the past, not the future? Why does a glass fall and shatter, but never unshatter? The answer lies not in the fundamental equations themselves, but in how we apply them, and in the concept of entropy. Entropy is a measure of disorder, of the number of ways a system can be arranged. And according to the second law of thermodynamics, entropy tends to increase over time. That's why time feels one-directional. It's not that the laws forbid backward motion, it's just that moving from low entropy to high entropy is overwhelmingly more likely. Break an egg? Easy. Unbreak it? Possible in theory, but unimaginably unlikely in practice. That's the arrow of time, emergent, not fundamental. A statistical tendency born from the fact that the universe started in a very low entropy state. But here's where it gets stranger. Not all physical processes are fully time-symmetric. Certain interactions in particle physics, specifically in weak nuclear interactions, show tiny violations of time symmetry. This is called CP violation. In these cases, if you reverse time and charge, the outcomes are not identical. This subtle asymmetry might even be responsible for the matter-antimatter imbalance in the universe, but these violations are incredibly small. For the most part, nature's laws don't distinguish between past and future. This has led some physicists to propose that the arrow of time is observer-dependent, that it's not a property of the universe, but a consequence of how we interact with it. The brain records memories in one direction. Entropy increases in the direction we call forward. But those are emergent patterns, not cosmic commandments. Some interpretations of quantum mechanics, like time-symmetric formulations, even propose that the future and past influence the present equally. That particles don't just respond to past events, but also to possible future outcomes. It's a radical idea, but it fits the math. In fact, in Feynman's path integral formulation, particles explore all possible paths through space and time, including ones that move backward. What we see is the result of constructive interference among those paths. The paths that cancel out don't appear in reality. The ones that align become the world we know. In that view, time is a dimension, like space. And just like we can move left or right, up or down, the equations allow for forward and backward motion in time. So then, what's real? Is the arrow of time fundamental, or is it just a reflection of our perspective, our thermodynamic context, our limited access to information? Some physicists believe that when we finally understand quantum gravity, the picture of time will change completely. That time may not be a fundamental ingredient, but something that emerges like temperature or pressure from deeper, timeless rules. And maybe that's why so many theories at the edge of physics, string theory, loop quantum gravity, timeless wave functions, describe a universe without a clear arrow of time. Not because time doesn't exist, but because it isn't what we think it is. So the next time you watch a movie in reverse or dream of turning back time, remember, the laws of nature might not mind, but the universe as we live in it moves forward, not because it has to, but because that's how the story began. Quantum fields in curved space-time, we're used to thinking of particles as the most fundamental things in the universe. Little bits of matter, electrons, photons, quarks. But modern physics tells us something different. Particles are ripples in fields. The electron is a ripple in the electron field. A photon? A ripple in the electromagnetic field. The entire universe, from light to matter to forces, is made of quantum fields. But what happens when those fields exist in a universe where space-time is curved? That's the strange and beautiful question behind quantum field theory in curved space-time. Let's set the stage. Quantum field theory, QFT, is the framework that merges quantum mechanics with special relativity. It's how we describe the Standard Model. It's how we understand particle physics. In QFT, particles are excitations in fields, and these fields live in flat space-time, the kind described by special relativity. But in the real universe, space-time isn't flat. It curves. It bends around mass and energy. That's the foundation of general relativity. So if we want to understand how quantum fields behave in the presence of gravity, we need to consider what happens when those fields live in a curved background. And that's exactly what quantum field theory in curved space-time tries to do. It's not yet a full theory of quantum gravity. It doesn't quantize gravity itself. Instead, it treats space-time as a classical, curved background and places quantum fields on top of it, like putting a vibrating string on a warped drum. And what do we find? Some of the strangest, most profound effects in all of physics. Let's start with Hawking radiation. According to Stephen Hawking, black holes aren't completely black. When you place a quantum field near the event horizon of a black hole, the curvature of space-time causes pairs of virtual particles to separate. One falls in, the other escapes. To an outside observer, It looks like the black hole is radiating particles, slowly losing mass, eventually evaporating completely. This isn't just theoretical. It's a prediction of quantum field theory in curved spacetime. It combines the smooth warping of Einstein's geometry with the jittery behavior of quantum fields. And the result is a black hole that glows. Another incredible result? The Unruh effect. If you accelerate through space, the vacuum of quantum fields doesn't look empty anymore. Instead, it appears warm, filled with particles. An observer standing still sees nothing. But an accelerating observer sees a thermal bath of radiation. Reality, it seems, is observer-dependent, even in the quantum vacuum. Both Hawking radiation and the Unruh effect come from the same deep insight, that quantum fields behave differently depending on how you move through spacetime and how that spacetime is shaped. It also means that the concept of a particle becomes fuzzy. In flat spacetime, it's easy to define a particle. But in curved spacetime, the definition of what counts as a particle depends on your reference frame. Different observers, moving differently, or located in different gravitational potentials, can disagree on whether a particle exists. Reality isn't absolute. It's contextual. This framework also plays a role in early universe cosmology. During cosmic inflation, the universe expanded at an exponential rate. Tiny quantum fluctuations in fields during this time were stretched across the cosmos, and those fluctuations became the seeds for galaxies, stars, and structure. The ripples in the cosmic microwave background, the afterglow of the Big Bang, are quantum fingerprints magnified by curved space-time. It's one of the most extraordinary connections in physics, quantum jitters, in an expanding universe creating the cosmic web we see today. But we're not done yet. Quantum field theory in curved space-time also helps us understand the limits of our theories. Because as we push into regions of extreme curvature, near singularities or the earliest moments of the Big Bang, our current tools start to break down. It's a signal we need a deeper theory, a full quantum theory of gravity. But until we get there, this hybrid framework gives us a glimpse. It tells us that space and time aren't just a passive stage. They shape how particles behave. They determine what energy means, what temperature means, what emptiness means. It's a strange world where the vacuum isn't silent, where acceleration creates warmth, where black holes evaporate, and where the tiniest fluctuations give rise to galaxies. Quantum fields in curved space-time reveal the universe as a living canvas, one where geometry and quantum behavior are entangled. A place where curvature whispers and particles respond. The uncertainty principle. There's something comforting about the idea that if you just look close enough, measure carefully enough, you can know everything. Where a particle is, how fast it's going, what it's doing, all the details neatly pinned down. But quantum mechanics breaks that illusion. It tells us that fundamentally, there are things you cannot know at the same time. No matter how good your tools are, no matter how sharp your mind is, reality has limits, boundaries. This is the heart of the uncertainty principle. Formulated in 1927 by Werner Heisenberg, this principle says something deceptively simple. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Let's pause on that. You might think of it like trying to photograph a speeding car. If you freeze the frame to see its position clearly, you lose all sense of motion. But if you blur the image to capture the motion, you lose detail of where exactly it is. Now apply that to the tiniest particles in nature, electrons, photons, quarks, and you're no longer dealing with camera tricks. You're dealing with fundamental reality. But the uncertainty principle isn't just about measurement errors. It's not a limitation of our tools. It's a built-in feature of the universe. Even if you had a perfect measuring device, the uncertainty would still be there. Why? Because particles in quantum mechanics don't have definite positions and momenta until you measure them. Until then, they're described by wave functions, spreads of probabilities. The sharper you make the wave function in space, the wider it becomes in momentum space. It's like squeezing one side of a balloon. The other side bulges out. That's the trade-off. Mathematically, this is expressed as h/2, where dx is the uncertainty in position, dp is the uncertainty in momentum, and h is the reduced Planck constant. This isn't just for position and momentum. There are other pairs of quantities with the same kind of uncertainty, energy and time, for example. Try to measure the energy of a system precisely in a very short time, and you'll get fuzziness. You can't pin both down at once. The deeper truth is that quantum properties are contextual. What you choose to measure affects what other information becomes inaccessible. And this changes everything. It means that the classical dream, the idea of a world with particles having exact properties at all times, is an illusion. In the quantum world, knowledge comes with consequences. You can learn one thing, but only at the cost of unknowing another. Let's take an example. Imagine an electron passing through a slit. If you don't try to detect which slit it went through, the electron acts like a wave. It interferes with itself, creating a pattern on a screen. But if you place a detector to catch which slit it used, the interference disappears. You've gained knowledge of its path but lost the wave behavior. That's quantum mechanics keeping its balance. This principle also has real consequences in the structure of atoms. If electrons could have both precise positions and momenta, they'd spiral into the nucleus. The atom would collapse. But because of uncertainty, electrons can never sit perfectly still. They're always smeared in space, and this smearing creates the energy shells that form stable atoms. Uncertainty creates structure, and it protects the universe from collapsing into itself. It also shows up in particle physics, where short-lived particles borrow energy from the vacuum allowed by the uncertainty between energy and time. These virtual particles briefly pop into existence before vanishing again. This is the quantum foam beneath reality, a bubbling sea of possibility always shifting. And perhaps the most profound consequence is philosophical. The uncertainty principle tells us that the universe is not deterministic. You can't predict the future with absolute certainty, even in principle. You can only calculate probabilities, likelihoods. Not because you're missing information, but because the information doesn't exist until you ask for it. Some interpretations, like the Copenhagen interpretation, say this is just how reality is. Others, like many worlds, say every possibility does exist, just in different branches of the universe. But either way, uncertainty is fundamental. It's not an obstacle, it's a feature. It's what makes quantum mechanics so radically different from classical physics, and it's what makes the universe creative, flexible, unfolding in unpredictable ways. So what does that mean for us? It means that knowledge always comes with limits. That precision is always a trade-off. That certainty is a luxury the quantum world doesn't provide. It means reality is not a perfect blueprint, but a living equation, a balance of what can be known and what must remain unknowable. And maybe that's not a bug. Maybe that's where all the wonder comes from. Because a universe without uncertainty would be a universe without surprise. Supersymmetry. Physics is full of patterns, particles that seem to come in pairs, forces that mirror each other, equations that hum with balance. But as beautiful as these patterns are, they're incomplete. For every known particle, for every familiar rule, there seems to be something missing, like half of the puzzle hasn't been filled in yet. That's where supersymmetry, or SUSY, comes in. It's a bold idea, a proposed extension of the standard model of particle physics. And it suggests something extraordinary, that every particle we know has a hidden partner, a secret twin we haven't seen yet. Let's slow down and unpack what that really means. In our current understanding, all particles fall into two categories: fermions. These are particles that make up matter: electrons, quarks, neutrinos. They have half-integer spin and obey the Pauli exclusion principle, which keeps matter from collapsing. Bosons. These are force-carrying particles: photons, gluons, W, and Z bosons, the Higgs. They have integer spin and don't obey the exclusion principle, which allows them to pile up in the same state, like photons in a laser. Supersymmetry proposes that for every fermion, there exists a corresponding boson, and for every boson, a matching fermion. Electrons would have selectrons, quarks would have squarks, the photon would have a photino, the gluon gets a gluino, the Higgs, a Higgsino. These partner particles are called superpartners, but if they exist, where are they? We've never seen them in experiments, not at the LHC, Large Hadron Collider, not in cosmic rays, not in particle collisions. So the most likely explanation is that they're heavier, much heavier than their standard model counterparts. Too heavy to have been created at the energy levels we've tested so far. So why do physicists believe in them? It's not just wishful thinking. Supersymmetry solves several deep problems in physics. Let's start with the hierarchy problem. In the standard model, the Higgs boson's mass is extremely sensitive to quantum corrections. Virtual particles constantly interact with it, threatening to push its mass to enormous, unnatural values. But if supersymmetry exists, then every particle that contributes to this correction has a superpartner that contributes the opposite correction. The result? A cancellation, a natural explanation for why the Higgs mass is stable and not absurdly huge. SUSY also helps with unification. At high energies, the strengths of the fundamental forces, electromagnetic, weak, and strong, almost come together, but not quite. Introduce supersymmetry into the mix, and suddenly, they unify. Their force strengths meet at a single point in what's called grand unification, a sign that all forces might emerge from a single force at high energies. Then there's dark matter. We know dark matter exists. We can't see it, but we feel its gravity. It holds galaxies together. It makes up about 27% of the universe, but we don't know what it's made of. Supersymmetry provides a perfect candidate, the lightest supersymmetric particle, or LSP. Stable, electrically neutral, weakly interacting, exactly the kind of particle that could be lurking all around us, making up the invisible scaffolding of the cosmos. So in one elegant framework, SUSY offers solutions to multiple mysteries: Higgs stability, force unification, and the nature of dark matter. It also fits neatly into string theory, where supersymmetry isn't just helpful, it's required. In string theory, particles are tiny vibrating strings, and SUSY ensures those vibrations behave consistently. Without it, the math breaks. But here's the challenge. As of today, we haven't found supersymmetric particles. The Large Hadron Collider was supposed to see hints: missing energy, extra jets, decay patterns, but so far, the results are silent. That's led some to question, is SUSY real? Or is it just a beautiful idea that nature didn't choose? There are alternatives, other explanations for the Higgs mass, for dark matter, for force unification, but none quite match SUSY's elegance. None wrap so many loose ends with a single thread. And so the search continues. Future experiments, higher energy colliders, underground detectors, astrophysical surveys may still uncover the superpartners we've been waiting for. And if they do, it would revolutionize physics. It would confirm that every particle has a hidden mirror, that nature is more symmetric than it appears, that our current model is just a shadow of a deeper, more unified reality. Even if Susie turns out to be broken, its symmetry imperfect, it could still leave behind clues, remnants, patterns in particle masses, subtle signals in cosmic radiation. Because supersymmetry isn't just a theory, it's a vision of a universe that's balanced, a universe where every force has a counterpart, every particle has a partner, a cosmic dance choreographed by symmetry itself. And maybe, just maybe, we're only one discovery away from hearing that music play.